So welcome to the second annual symposium of the Dartmouth Symposium on Climate, Energy, and Society. My name is Angie Hofmann. I am the one who tested most of you for the slides and titles. And I'm filling in for April Salas, our executive director, this morning because unfortunately April got COVID on the way traveling to Dartmouth. So we'll not be able to be here in person today. But it's my pleasure to welcome all of you to this event, and I'm hoping that it's going to be really meaningful for you and also exciting at the same time. We put this symposium together to bring attention to, of course, the climate crisis, to engage the community, to encourage you to collaborate, to create new knowledge, and to find implementable solutions for the climate disaster that we are facing. At the Irving Institute, we don't just do the symposium on this once a year, but this is an ongoing process. We also have other programs and initiatives that take care of this or deal with this topic. For example, we have a faculty advisory board that meets on this and gives directions to a strategy. We have faculty affiliates program, and part of that, for example, you get to have access to priority access to our facilities. They also get newsletters and bulletins on a monthly basis. They get sometimes seed funding for hub-related or priority-related projects, and so on. Then we have monthly seminar series that feature the research of 2 faculty members each month. And I should probably advance my slides here so you can see this a little bit. And we have working groups that we put together on some select topics and financial administrative support for our affiliates as well. And going forward, we also have a new accelerator program that is a 3-month program that teaches startups internally, also externally, about entrepreneurship and climate. What I want to announce today is going forward, at the end of this month, we also have a new relaunched seed grant program for faculty that will start in the fall. There will be an information session coming forward. There's up to $100,000 for projects that you can garner with an application and pitches. And so I invite all of you to pay attention to the announcement and the information session on that. That's across campus. It's not discipline specific. It is really something that anybody in any discipline that has a valuable idea can apply for and participate in. At the same time, I also want to announce that we have planned a new symposium in the spring. This one is internal. The one in the spring will be bigger. It will be including students, and will also include external speakers and participants. So we will see more on that information as well. I don't want to take too much more time because I know we are tight on that, and I want to give you over to Barbara Will, our vice provost, that will oversee Irving and will give us opening remarks today before we start with this faculty presentation. So,
Thanks so much, Angie. Hi, everyone. I have to be in my car in about 5 minutes, but I'm coming back. So these will be very short remarks, but this is just a chance to welcome you on behalf of the Provost's office at Dartmouth to a really exciting day. Many of you were here last year when we had this day on climate, energy, and society. And I think we all are agreed that not much has changed in the past year, except if anything, things have gotten worse in terms of climate news. For example, we had the hottest day on record in the world on July 3rd, but it was broken on July 4th, and then on July 5th, and then on July 6th. And although ironically, this year is predicted to be one of the coolest for this generation to come. We've seen unbelievable flooding in New York City and Libya. We've seen climate damage measuring about $1 billion in the US alone. So these are just dark facts to start our morning, but I think you have many more that you could add. So why are we here? We're here to talk about this, and we're here to talk about solutions. We recognize that there is a climate emergency, but this is also the time to act. And so what we're doing today is hearing about all of the amazing and diverse research projects that are being done by our faculty here at Dartmouth, their predictions for the future and their ideas on potential solutions. And one of the goals of today is for you to hear your colleagues and think about potential collaborations between yourselves and also between colleagues at other institutions as well, because of course this is a pan-institution issue and project that we're engaged in. So we hope that this day will be a call for further engagement across our campus and beyond. And I think it's going to be really exciting to hear both some of the people that we heard last year and where they've come, and also some new voices as well. So I welcome you, and I'm going to turn the podium over to our first speaker for our first round of lightning talks. And that's Mary Albert, Professor of Engineering, and she'll be launching our day. So thank you very much.
So, as you know, everybody gets about 3 minutes. I will be timing, and if you get a little chime go off, you have maybe about 20 to 30 seconds left to exit the stage and go back to your seat before the next person comes in. Mary, you're okay.
Thank you, and good morning to everybody. Thank you for coming. I'm Mary Albert. I'm a professor of engineering at the Thayer School, and this project is one of my projects funded by the National Science Foundation. This one is a collaboration between faculty and students at the Thayer School and Indigenous hunter-fishers in Northwest Greenland. The people in Northwest Greenland have a long heritage of hunting and fishing in the area. They have, the people there now are the direct descendants of people who have lived there for over 900 years, adapting to climate and adapting to new conditions. Moving on to the current climate is one aspect of what's affecting them, but society and other things are as well. After working with them, this is a co-generation of knowledge, and our research is based on their needs. So it's a collaboration from the start, including before the proposal was written. And it boils down to, there are two sort of very practical items, that the current energy system in most of Greenland, especially in the small communities, is totally based on diesel fuel. All renewables are centered in the larger cities with hydro. So the cost of energy in Qulleq and Scheideler and Northwest Greenland is expensive. It is also based on fuels that must be imported. And the energy costs have risen. At the same time, the cultural heritage is very strong in these areas. They are subsistence folks, but they also have a small cash economy. And the current problem is that the income that they receive from fish, they fish through the ice for halibut, is not enough to sustain their families. Their spouses have to have other jobs, and we're seeking more of a balance. And so in this project, we are working with them to co-generate knowledge and to take action. We're partway through the project now. What we've discovered so far is that adding renewables can not only lower their energy costs, both on the municipality level and at the local household level, but also it leads to increased self-reliance. These communities have always lived on the margin. Not being reliant on the outer community is very attractive to them, and they're capable too. So we've done the modeling and research to show this, and that's published. We found that affordable, energy efficient small homes will reduce their energy costs through energy conservation. In Qulleq area, the homes that these people live in now were designed in Denmark, sent up as kits. They're not suitable for the community either in terms of the style of the home or in terms of their energy sort of lack of efficiency. They're expensive to keep. We have worked with them to co-design a new affordable small home that meets their cultural needs, that is attractive, and that they will be able to afford as their older homes, as they overturn the older homes. Now, on the other end of the thing, how can we help them to increase their financial income for the fishers? As again, they fished for for many centuries, and the fish that they catch are some of the finest, high quality halibut in the world. The waters that they come from are some of the most cleanest waters on the planet. This is a high-end product that currently they sell the whole fish to a major industry for a small amount of money. We've worked with them to identify 3 different ways that would be possible in the future for them to increase the income to the fisher for their catch. One is selling the fish to Thule Air Force Base. Another is a boutique market selling high-end fish, think organic vegetables, to a higher end market. And finally, drying the fillets. Technology to be able to dry the fish on ice that they could sell them at a high price to home markets within Greenland. So we're continuing on this project, and it's thank you for coming.
Hawley is nice.
Thank you.
We have some time to anybody wants to microphone.
Great. Well, good morning, and thanks for being here. What I thought I would do, rather than specifically describe a specific project, was to, in 3 slides, try to tell you a little bit about what my lab does. I am a physical glaciologist. I'm in earth sciences, and my students and postdocs and I spend most of our time thinking about large-scale process and small-scale process, mostly on polar ice sheets. And so, to try and divide this into 3 slides, and also not to put too many bullets on the slide, I figure a picture is worth 1,000 words. And I'm going to give you about 15,000 words in this talk. So to begin with, we do a lot of remote sensing in our work. And this is to make our ice sheet process studies large scale. And we also go down to the small scale. So on the left, you can see, or rather on the right, you can see that we're working with radar remote sensing from satellites. We also use spaceborne lasers. And this results in large scale volume change of Greenland, and also large scale mass balance studies. Coming into a smaller scale all the way on the left, we also do airborne radar remote sensing. And this allows us to measure specific mass balance at certain parts of the Greenland ice sheet over time. And then right in the center, we're even going to the smaller scale of drone-based studies. And this allows us to look at such small scale events as drifting and wind deposition of snow and ice and how it's redeposited. So remote sensing gets us really the big large scale picture, but there's also things that you have to do in situ. So there's lots of things that we do in remote sensing that have to be validated on the ground. So there's kind of 2 main reasons that we'll go into the field to get our boots on the ground. One is to validate the remote sensing measurements we measure, and the other is to get measurements that we would otherwise be unable to do remotely. So this is a pretty busy slide. So I'll kind of like go through it a little bit with some examples. So some examples on the upper far right, we're measuring the forcing conditions of the ice sheet. So here we're measuring wind speed, we're measuring temperature, we're measuring temperatures deep into the ice, which you're again unable to measure remotely. All along the bottom, this is a project in which we drilled boreholes through 700 meters of ice to measure what was happening in the subglacial water system. Again, this is something very difficult to measure remotely, and so, well, it's actually very difficult to measure in situ as well. Continuing clockwise around this frame, we measure surface elevation with high-quality GNSS, which is a superset of GPS equipment. To measure surface elevation, this is something we did remotely, right, with a satellite, but it's important to have ground truth and validation for these. We've actually contributed a lot to the validation of both NASA and European Space Agency satellites. Finally, to get a better picture of the spatial variability of this accumulation, this is one side of the mass balance equation, which is the health of the Greenland ice sheet. We've taken this long traverse around the ice sheet and measuring a bunch of different things. But in particular, I'm showing what we did with ground penetrating radar. And so this images subglacial, or rather subsurface horizons, which are each former surfaces. And this allows us to measure accumulation at a very detailed spatial scale. So all of these things that we measure in situ require specialized instrumentation. Some of that instrumentation is easily commercially available. Some of it is not. And the main reason it's not commercially available is nobody actually wants to make this measurement except me and a handful of other people. And so therefore, people who have the technology to build it wouldn't build it because they want to sell it to a lot of people. And so for that reason, another big thrust of my lab is developing novel instrumentation to actually enable us to make these measurements. And so again, I'll just highlight a couple of different projects. And as I said, these are not technologies that are completely new. It's just we're implementing them in either a much more cost-effective way or a way that works for us. So on the right-hand side is a set of borehole tilt sensors that we built to measure tilt in the glacier. This allows us to understand better the rheology of the ice as the ice deforms under its own weight. I'll finish this really quickly. The main reason for us to develop our own ones of these is geotechnical firms have these, but they cost $25,000 a piece. And we were going to lose these inside the glacier. So we made these for about $35 a piece. More importantly and more exciting to me is a GNSS instrument that we've just been developing. We call it an Ogre, which replaces a commercial $50,000 GPS unit with something we built in the lab for $250. More importantly, it only takes milliwatts of power. And when you're out remote places in Greenland, you need to be very, very power efficient. The commercial system has a box about this size, which is about half the size of this table. And our new box is about this size. So we're able to do this in a much more efficient way. And importantly, we have released all of these designs as open hardware and open software on GitHub. So thanks very much.
Hi, guys. Nice to see you.
Hello, everyone. I'm Margaret Karagas. I'm professor and chair of the Department of Epidemiology in the Geisel School of Medicine here. I study kids. Children contribute the least to climate change, but are the most affected. So this is a figure. We have a pointer here. Oh, that's what I'm putting. The figure here is from a recent New England Journal of Medicine article by Karen Edu and Ricky Ferrara. And Ricky has also written a book recently on children's health and the peril of climate change. So what we do specifically is we study rural kids. Rural kids are understudied in epidemiologic research, and the factors that they're exposed to are different than city kids. And we know very little about this. So our job is to look very holistically at the drivers of lifelong health, including those that are contributing and are consequent to climate change. So it's important that we generate the data to inform the mitigation and adaptation strategies, and then to test these strategies to see if they're actually effective. And you'll hear more about that from Jeremiah Brown this afternoon. So what we have is we have studies of over 3,000 pregnant people and their offspring here in northern New England. We're following them to age 18 and even 21 through the New Hampshire birth cohort study. And we contribute to a study of over 55,000 children in the US through the NIH director-funded ECHO program, which is the environmental influences on child health outcomes. And we just got renewed for another 7 years. And so what are our methods? They're very interdisciplinary. They involve people in the room here, Shrim and Celia. For example, we have a wristband sensor that measures over 1,000 endocrine disrupting chemicals. We do metabolomic assays. We're looking at spatial imaging. This is a figure from placenta from Tracy Punchin. We're looking at early ultrasound. We have sensors that we put in the home during pregnancy that can measure the nanoparticles in air that are coming from wood stoves related to energy. We also put personal monitors on small children. We study the microbiome. We can look at their fat mass through DEXA scans and through Shrim and Jonathan Shipman. We've done some geospatial analyses. We study teeth in the lab. And during the pandemic, of course, we had to develop all kinds of methodologies to assess kids in their homes, like their lung function that we can now evaluate remotely. And then we use a number of artificial intelligence methods to look at the phenotypes of children's neurodevelopment and their growth trajectories. So we're very interested in collaborating with you all. I'll be doing a Fulbright this winter in Athens. Greece has been terribly affected, as we know, through the impacts of climate change. So I'll be focusing on children's health and climate change there. So I'm happy to meet everybody and tell you more about our work.
Next person, Erin Mansur.
All right, so I just want to tell you a little bit about one paper I'm working on right now. So I'm Erin Mansur. I'm in the business school here at Dartmouth, and this is co-authored work. And what we're interested in this paper is looking at whether it's feasible and what would the cost and benefits be of immediately stop using coal to produce electricity in the United States. So just a couple of slides. So first, why is this important? Coal is the major contributor to air pollution, local air pollution from power plants in the United States. It's a major contributor, of course, to climate as well. And a number of countries have signed an agreement to set target dates of when we could phase out coal. The US hasn't done that yet. A number of states have made their own commitments. But we want to know, just given the capital today, what could be done right now with reducing our dependence on coal? Could we ban coal? If not, could we use a whole lot less of it? And if so, what would be the cost of this? And what would be the co-benefits? So just to give you an idea before we get to the methodology of what a ban would look like from an economics perspective, we can think about the amount of electricity that is being generated from dispatchable technologies like coal and natural gas. You think about that as our net load. Far on the left, that is going from zero coal to all coal. The other direction is natural gas. Where the two marginal cost lines cross, that's the market equilibrium without any environmental regulation. Where the two dotted lines cross is what would be efficient. And so if we're at the point where we're using some coal because we're using electricity markets, and we want to get to the point where the dotted lines cross the social optimum, typically we talk about Phaseout taxes. So instead of doing that, what if we just ban coal? Would that be welfare generating? Well, we gain the green area, but we go even further. We get then we loss of the red area. So it might be a winner, it might be costly to society, and that's what we wanted to try to get a sense of in the trade-off. So what we do is we match coal plants. We find every coal-fired power plant that's generating electricity every hour of every day in the United States, match it to a nearby dispatchable technology, mostly natural gas, and look at whether we can swap out that production and check to make sure that this passes what we call a revealed preference check to make sure that the substitute unit actually has a higher marginal cost. Otherwise, why wasn't it producing in the first place? What we're thinking about this is giving priority dispatch to everyone but coal, basically. What do we find? Well, first, we find that a ban is not feasible. Not surprising, there's a lot of parts of the United States that use a lot of coal. Upper Northwest as a region, the Midwest in particular, would see rolling blackouts most hours of the day if we were to ban coal immediately. However, if we just changed the priority and said, okay, we're going to dispatch all technologies except for coal first, we'd see we could reduce between 60 and 90% of current coal generation overnight without any additional capital investments. This would reduce about 20 to 30% of the carbon emissions coming out of the electricity sector. It would cost between $40 and $70 per ton of carbon reduced. Not to mention massive co-benefits. So again, co-benefits, I mean, local air quality, right? Local air quality would improve. It would put economic dollars on that. That would be even greater value than these costs. Thanks.
Uh-oh. Comment.
Too much technology. Okay, for 3 minutes. Anyway, hi, I'm Celia Chen. I'm in the Department of Biology, and this is not my slide, but the side, Nancy.
Other way.
Oh, the other way. Sorry. Okay. Yeah, I'm an aquatic ecologist, so I study lakes, streams, estuaries, and rivers. But mostly what I focus on are contaminants. And with people like Margaret, Karagas, colleagues have studied metals, mercury especially, in aquatic systems for many years as part of the Dartmouth Toxic Metals program. And then more recently, we have started to really focus on the emerging contaminant PFAS, which is per and polyfluorinated alkyl substances. And we are currently working in areas in the Gulf of Maine, Great Bay Estuary, in New Hampshire, in the southern New Hampshire lakes, Lake Champlain, and tributaries. And the reason we're working in so many, probably too many places, is because the amount of grant calls that have come out over PFAS. If you haven't heard of PFAS, you should watch the movie Dark Waters with Mark Ruffalo and Anne Hathaway, or the documentary called The Devil You Know. Just putting that out there, that's your assignment. So, and it really is an incredibly pervasive and persistent pollutant in the environment. It is now known to cause many human health effects, including effects on the immune system, thyroid, and effects on reproductive health, as well as cancers. So it's, and as we study more, we learn more about what the effects are. The other reason that it is really important to study PFAS is because, guess what? It's in everything we use. It's in your stain-proof carpeting. It's in your Gore-Tex outdoor gear. It's in your, fortunately, people don't use Teflon pans anymore, but Teflon is PFAS. It's also in aqueous firefighting foams, which have been used all over the world, and many Department of Defense sites, as well as airports. So anyway, it's kind of everywhere, and it's unlike other contaminants that many of us have studied that show up at very, contaminated sites. There are contaminated sites with PFAS. Okay, so our work though has we've just been finishing a project where we're looking at the exposure of humans to PFAS through seafood. And in fact, it is one of the biggest sources of PFAS exposure from food. The other big source of exposure for PFAS is drinking water. And you may have heard there's sites all over the country where it turns out their groundwater systems have been contaminated by PFAS for many, many years. We are working at in Great Bay, New Hampshire, in case you don't know where that is, it's near Portsmouth. And there is the former Pease Air Force Base there. And we have been looking at shellfish and sediments and water around that site. We also had a sample set for which we had been studying mercury, where we have inshore and offshore demersal fish, including things like hake and skate and cod, and been measuring PFAS in those. The interesting thing for someone like me as an ecologist is that there are over 8,000 compounds. We now currently measure 40 of them, and they range in carbon chain length. And the carbon chain length determines their persistence in the environment and how much they're bioaccumulated by organisms and how much they biomagnify. And so it's really interesting. I'm not a chemist. I work with many chemists, thank goodness. And it's just an interesting way to look at food webs. Which ones get taken up and biomagnified into the fish that we eat. So we've been doing this project that's kind of, we're in the pulling the data together, writing our papers mode. But as I said before, we have a lot of different projects, and we've started to, this past year, work on southern New Hampshire lakes where we know there's PFAS in fish. And we're going back to Great Bay, where we have sampled around wastewater treatment plants, which are known to be a source to aquatic systems. So thanks a lot.
No, Tyler.
Perfect. The introduction. Hi everyone, I'm Scheideler. I'm at the Thayer School. I'm a fifth year assistant professor there. And I'm going to tell you a little bit about our work in scalable nanomanufacturing of energy materials. We specifically work on energy technology, so the way that we generate energy, the way that we convert forms of energy. And if you look at different energy technologies, semiconductor devices are really sort of this critical piece of a lot of those. So that's essentially describes the intersection here, what we do, which is device physics, semiconductor device physics, material design or energy materials, and then how we scale them up. So how you go from something that you make at the lab scale in very small quantities or very small areas to something that you make at the scale of energy technologies like a solar panel at the meter scale. So we work on a number of different topics. The themes and the sort of material that unite all those are metal oxides. So we work specifically on different inorganic metal oxides that are used in solar cells, that are used in electrodes for electrocatalysis. So I'll tell you first about our projects in solar. So in solar, the specific material system that we work on are metal halide perovskites. And if you've heard of metal halide perovskites, it's because they have a lot of really fundamental material properties that make them attractive for scaling up solar production to the terawatt scale. So from sort of a fundamental material perspective, they have this crystal structure, this ABX3 perovskite structure that gives them immunity to a lot of sort of intrinsic defects in the material that makes them less sensitive than something like silicon. Sort of the important thing about that is in the case of silicon, you have to actually refine it to be the most pure substance known to man before it works well as a solar cell. This material, on the other hand, is sort of quick and dirty. You can make it at low temperatures. You can make it without high purity, which means you can actually make it at a much lower manufacturing cost. So if you want to drive down the cost of sort of installing additional solar in the grid, this is one of the best ways to do that. One of the other really interesting things about it is that there are really a huge variety of chemistries that you can use to make this material. And in doing so, you can control properties like the band gap energy. So it's possible to make multi-junction solar cells that sort of compete at the same levels as 3-5 cells. So if you're familiar with the multi-junction technologies that are used in space, you can get really similar performance levels, but with essentially an order of magnitude lower cost in these devices. And the approaches that we use are actually far not from the semiconductor device industry, because I said that these are not sort of traditional materials like silicon where you need vacuum deposition. Instead, you actually have to look to technologies like the graphic arts, where they essentially can make materials over meter squared areas at sort of pennies per unit. So the technology that we use is this flexographic printing method, is borrowed from the graphic arts. We're pushing it to another level. So graphic arts doesn't necessarily care about nanoscale uniformity. That's something that we have to focus on, essentially understanding the rheology and the precursor chemistry of these inks to be able to design materials that we can pattern with essentially sort of sub 10 nanometer uniformity over large areas. And we can do that. We can form solar cells. So we make devices in my lab. We make solar cells that recently have hit sort of efficiencies that are essentially at parity, although at lower length scales than silicon, but at parity with the performance of commercial silicon. All right, now I'll tell you about one additional topic. So I said that we focus on metal oxides specifically. Metal oxides have a number of different applications. One of the really interesting ones is as an earth-abundant catalyst material. So if you're familiar with electrocatalysis for producing hydrogen, the state of the art for that is actually using platinum group metals like platinum and iridium to generate hydrogen through electrocatalysis. But it turns out that that's really tough to scale up because those materials are scarce and they're incredibly expensive. Transition metals can give you a lot of the same benefits, albeit with some additional problems related to their stability in these sort of harsh and corrosive electrochemical environments. And the approach that we take is actually use scalable manufacturing technology. So technologies like additive manufacturing that give us control, not just over the chemistries of these materials, but also their microstructure. It turns out that that's actually a really key piece of information you need to design efficient catalysts, because you're actually dealing with this mass transport problem, essentially getting bubbles out and electrolyte in to be able to generate large amounts of hydrogen. So if we're going to tackle this problem that the DOE's given us, essentially in the next 10 years, we want to make hydrogen 1 kilogram for less than $1. We have to go with more scalable technology just like this. So happy to take any other questions during the break later on.
What's that mean?
Okay, perfect. Hi, everyone. My name is Sneddon. I'm in the Department of Geography and the Department of Environmental Studies. And I'm presenting this presentation on political ecology of pumped storage hydropower. Political ecology is a field emanating from geography, anthropology, and environmental studies that basically looks at the political and economic drivers of environmental transformation and different actors that are involved in producing some of those drivers. So I just wanted to point out, this is a 2021 report from an international forum on pumped storage hydropower called Pump It Up. And that seems pretty self-explanatory. I became interested in it as someone who studies the hydropower industry going back a century and looking at large dams around the globe. The amount of media attention and boosterism, if I can call it that, around pump storage has just been phenomenal in the last 3 or 4 or 5 years. What's the basic idea of pump storage hydropower? It's pretty self-explanatory. During times of low demand and inexpensive electricity, for example, in the nighttime or off-season in certain locales, water is pumped from an existing reservoir to a secondary uphill reservoir where it can be stored and subsequently released to generate electricity during peak demand when prices are high. Couple of important points. Again, I'm just starting this project, so I would love to have some collaborators, especially people who actually can let me know about the economics and the technology involved in pump storage. It only makes sense in economic terms. The amount of power that is used to pump the water uphill is more than the water that is produced by, or the more than electricity that is generated when it was released downhill. But it makes sense in economic terms because of the shift in prices. So 95% of all current utility scale storage in the United States comes from pumped storage projects, and nearly all USH plants in the US are owned by utilities and private companies. So a couple things to just keep in mind. And again, just to give you a sense of the promotion that I've talked about, again, a lot of the promoters of pumped storage hydro call it the ideal clean green battery. They're emerging in massive markets for energy storage worldwide. I won't go into the details probably because I don't know them as well, but there are a lot of debates back and forth just what exactly are the most energy efficient and cost-effective technologies for storing energy in the United States and globally. And again, part of the appeal of pumped storage is that it can sort of provide ancillary services that can be integrated pretty well with solar and wind-oriented electrical systems as a sort of backup. And just to give an idea, I think I was at a hydropower conference recently, and pumped storage has this kind of inferiority complex. I heard a conversation in the restroom comparing pumped storage hydropower to the offensive line on a football team. They're really critical to the team, but they don't get much media attention. So there's this effort to kind of, again, boost up, get the hydropower industry to take, give more attention to pump storage, but there are big significant blocks, including local resistance in certain locales to pump storage hydro projects, as well as the FERC licensing process, which can take a long time, and it can be a risky investment. However, there are things like the recent passage of the bipartisan infrastructure law in 2022 provides $909 million to the hydropower industry through research and development programs administered by the Department of Energy. So the hope for pumped storage hydropower can get a chunk of that. So what are my research questions? And again, these are just a couple of selected research questions. How wide do social conflicts coalesce around renewable energy projects in the United States? Can we use pumped storage hydro project as a window into that process? We've sort of seen some resistance, right, in criticisms of wind and solar, biomass, et cetera. Why and how and who are the questions that we're asking in terms of pumped storage hydropower? What are the stakeholders engaged in such conflicts, and how do these conflicts evolve over time? Great. One of the things we're trying to do is is map out some of the pump storage projects, both the operating, the ones that have received licenses from FERCs and the permit process. And one of the things that maps like this allows us to ask is all kinds of interesting questions, such as what are the socioeconomic, biophysical, and political characters of storage hydropower locales around the country, and what are the processes producing those patterns. Thank you very much.
All right.
Great. Yeah, so hi everyone, I'm Laura Ray, we're professor at the Thayer School, and this is some work that my student Adam Grunwald and I started about 1.5 years ago, sort of a COVID related pivot. Oops. You all eat food, and you may not know in detail how it's grown, but this is a picture of a large sprayer fertilizing the field. You notice the sort of fog rising up. That is fertilizer that's lost. About 50% of what's applied is lost in the environment. Additionally, agriculture costs a lot of energy. About 23 equivalent gallons of diesel per acre is used, both in production of the fertilizer and applying it. Heavy equipment. This is the elephant in the room. We don't talk about the impact of heavy equipment on the field, compacting the soil, causing poor drainage of water, overwatering, etc. And then finally, the big problem we are facing is that the world population will require an increase in productivity about 60% by 2050. We're not on that. That's a 2012 statistic. We're nowhere near that timeline. So our research, we started out knowing nothing about agriculture, and we started to become somewhat experts. This is a corn plant. As it grows, it takes up the nutrients. Not all at equals zero. You don't feed your infant gallons and gallons of milk when it's born, but over time, in the sort of most significant growth phases, where it needs the nitrogen, those nutrients. And so we're applying it here, and it's all lost. So we want to do more with less. We want to be able to increase productivity with fewer resources. Another interesting problem here is that, you may have heard this in the news, farmers don't have a right to repair their equipment. That's a big problem for them. So what's our solution? We do robotics, and we'd like to replace that 20-ton tractor and sprayer with some small robots that manage and spoon feed row crops, so delivering the nutrients when needed. So this is kind of a conceptual design, but if you can do some simple analysis, you can show that with 40 or 50 robots, small robots, working in a field at very low speed, very low energy, very low ground pressure, you can manage this over a season, applying the fertilizer when it's needed. Less energy is used, lower ground pressure, less effect on the soil, less fertilizer, higher productivity, placing that equipment back in the hands of the farmers. So we did a study last summer to try to sort of assess the value of distributing fertilizer. We took an acre of land and working with a farmer in Orford, and we divided it up and did different trials where we put 80% and 100% of the base rate of nitrogen on different plots, either all at once at the beginning of the season, split twice early in the season, or distributed 5 times over the season, all by hand, very difficult experiment, and found that statistically nutrient content of the silage from distributed fertilization was greater than single or split early season. Ears of corn had 7% more kernels for distributed application, and there's no difference between providing 80% of the nitrogen over the season versus 100%. So we sort of did more with less. So going forward, our hope is that we can develop the technology that make this work, and to sort of change the face of agriculture from large heavy equipment to smaller robots. Thank you.
We need automation.
Terrific. So it's nice to be here. My name is Jack Wilson. I'm a senior lecturer in studio art and engineering science. I'm an architect. My background in terms of education is art and architecture. But through my interest in architecture, I've become extremely interested in engineering and the collaborative nature of working together with extremely intelligent and wonderful consultants and collaborators. I started my career working on large-scale institutional planning and designing construction projects, and I began teaching in the mid-90s here at Dartmouth through studio art initially, and then eventually with the engineering program. I'm really interested in art and committed to the importance of art, and I'm really interested in the integration of art into all of society. So about 12 years ago, Dartmouth mounted a pretty significant initiative in Haiti to help recover from the earthquake of 2010 there. And I was recruited to go down after kind of the initial disaster relief projects through collaborators at Dartmouth to work on community redevelopment and trying to understand how a place like this that's full of privilege can operate within communities that that need help, but from whom we can also learn. And it was really eye-opening to me to see conditions that a majority of the population of the world live in, and in this case, only a 2-hour flight from Miami. So I've been working there consistently since that time. With the beginning of COVID and kind of the dissolution of the social network in Haiti, we haven't been able to go back there recently. But I've made over a dozen trips there with students and teams. And we've worked on a lot of really interesting community development projects with some extraordinary people, both through Haitian nonprofit organizations and American nonprofits. But I really, I'm here to talk today about a parallel project that I've been working on, which is also focused on redeveloping craft and tradition into kind of 21st century technologies. And that's where the energy and society component comes in. My work has really involved a lot of disparate groups of students from Tuck School, from Thayer School, from studio art, and from the design practices. This is a group of students who spent 6 weeks in Marrakesh, Morocco, working with Eric Van Hove, an artist who came here initially in 2014 because the Hood Museum purchased a work of art of his, and so we've been collaborating since that time, bringing students into the process that he engages in his studio, and he's become incredibly interested in and committed to the preservation of cultural traditions in the workforce in Haiti. And so he's working with a large group of artisans now to transition from making essentially goods for tourists to buy to making an electric motorbike to begin with, and then hopefully more products that are like this to market to the workforce there. So we've been working with him on an ongoing basis, and have had him back. He was initially here as an artist in residence with the studio art department. He then came back as a Montgomery Fellow for a term, and we began to introduce him to lots of people around campus, and he became very interested in collaborations with Dartmouth. In 2018, we mounted an exhibition that featured a lot of the work that the students had done in collaboration with Eric, and he's made a kind of a progression of the Majuba, which is the name of the project, the Majuba Initiative, to begin to bring it to a condition where it can be scaled up to the market. Right now, he's created a collector edition of 100 bikes that will help him finance the project. And he's collaborating right now with students from the Dolly Lab on creating some apps. One would be an interface between the controller for the bike and the rider, and another is to help the workforce collaborate together. Thank you.
Morning, everyone. I'm Paul, gastroenterologist at the PA Reduction and Prescribed Medical Centers. And I'd like to shift our attention, or focus our attention to healthcare and the situation with climate change. So I think there's this interrelationship between climate change, the effect on health, and the strain that the effect on health and the increased needs for changing needs puts on the healthcare system. But at the same time, healthcare also contributes to climate change. So in the US alone, the healthcare system or sector generates 8.5% of greenhouse gas emissions in the US, 4.4% worldwide. So by this emission, we as physicians contribute to the harm through climate change, global warming of our generation and future generations. So there's a responsibility and moral obligation for us to help mitigate those issues. So I work a lot in endoscopy, so we're doing those procedures like colon cancer screening by colonoscopy. And on the right-hand side, there you see Kaylee, who's going to talk after me. At the end of the day, doing a waste audit in one of our endoscopy unit rooms. So this is the waste that we produce, and it's actually triggered me to go into this area and trying to understand how we can decrease our waste and our environmental impact. So we have an ongoing study where we try to understand the carbon footprint of our endoscopic procedures, and by doing so, identify and implement and assess actionable practice interventions. So I just want to highlight the complexity of that task. That's a boundary map that includes all the components of an endoscopic procedure that you have to look at to do a life cycle assessment or carbon footprint analysis. I'm not going to go into the details, but it covers scope 1, 2, and 3 emissions based on the greenhouse gas protocols. Scope 1 emissions is all those that are directly emitted through our work. In this case, it would be like anesthetic gases. Scope 2 emissions are those coming from energy or heating, ventilation, air conditioning use. And scope 3 emissions are all the rest, which in healthcare makes up 70 to 80% of all greenhouse gas emissions. And so they include, for instance, supplies and reprocessing activities of those instruments that we can use repeatedly. And so, as you may know, we switched or changed over the past 20 years from reusable instruments to single-use instruments for the most of the things we use. That's why we have this mountain of waste at the end of the day that's all landing up in the landfill or being incinerated or autoclaved. But to understand the carbon footprint of those instruments, so we have to go into each of those instruments and understand the carbon footprint, which we are currently doing. So we're working on an endoscopy instrument inventory. And that life cycle assessment, just for those who don't know, it takes all aspects into account from the manufacturing of an instrument to the disposal, so from cradle to grave. So there are several components to doing this analysis: the inventory, the energy, HVAC situation, and reprocessing. And so just to give you an example, the inventory, we have a working group that's also supported by international other teams that's trying to come up with those inventory and trying to calculate the carbon footprints using standardized approaches or methods. And here's just an example. For instance, at the lower bottom, you see different syringes. The carbon footprint is about 259 ranges by size of syringe from 19 grams to 132 grams. Of course, it doesn't really mean much if you've never thought about carbon footprint, but overall, the most important things of doing this is what are the hotspots that we can identify to reduce our impact. So comparative assessments are eventually the idea. And this has been a major challenge for us doing the HVAC and energy calculation within an endoscopy unit, because that's a dedicated space within the big hospital. So how do you do this? Well, we were lucky to partner up with Arup, which is a company that's has the headquarters in Denmark, but they also have international offices, and they were actually the main supporting company that helped with the global healthcare carbon footprint that was published in 2019. And they came to our endoscopy unit and took all kinds of different measures and came up with the first pilot model that you see there and with an Excel spreadsheet. So you put in different model inputs, and then it kind of creates the carbon footprint and also a cost, for instance. And then you can change the inputs. For instance, if you change from LED lighting or from fluorescent lighting to LED lighting, you have a decrease in 9% of carbon emissions, and you can do this for other inputs. So I think the idea of this model is to help other endoscopy units in the country to use it in their own unit, and then to put in their own variables so that they have a baseline, and then identify their hotspots in their endoscopy unit, and then to implement changes. So that's all we have. We can continue with some details on our audit. Thank you.
Anyway, it's the last speaker for the session, and then we have a 15-minute break.
Hi, everybody. My name is Kaylee. I'm an MD PhD student at Geisel and have been lucky to work with Dr. Hydropower to do the waste audit. So we measured a lot of trash. It was pretty crazy. We got about a ton worth of trash within 1 week. And we did a lot of different things with this. So ultimately, we weighed all of the trash. And so just to talk about like why we focus on endoscopy first, there's 18 million endoscopic procedures each year in the United States. And you figure each one is generating around 2 kilograms of trash, then that's a lot of trash. And it requires a large amount of energy to do an endoscopy. Each one uses predominantly single-use disposable materials. And it's the third largest waste generator in the hospital. And so that's why we ended up focusing on it. Dartmouth Hitchcock alone does 11,000 endoscopic procedures a year, which is a significant amount of contribution to our local landfill. As you can see here, I didn't actually put a lot of data on the slides, but we measured municipal biohazard and recycling. And most of the trash goes into the municipal waste, and not a lot of it was being recycled. And then a large amount of the weight is biohazard. And so some of the things that we wanted to think about throughout this in this waste audit was, what are we actually going to do? What are the outcomes? And this ultimately fed into what Heiko had just talked about with informing the disposal. So the end of the life cycle assessment, we had to figure out how much waste are we actually generating and where is it? And so we measured waste in all of the different endoscopic rooms. We broke it down into advanced versus basic procedures and found that, as you would expect, advanced procedures generate more waste. Oops, sorry, is that me? I'm like, then a basic procedure. And we also sorted. So we sorted one room every single day for 6 days. And basically, these are some of the things that we found. So you can see that the canisters, that's basically what the fluid that gets pulled out of the colon goes into. And that has to be incinerated. And so some basic things that I didn't think about was that incineration generates more carbon emissions than does going just directly to the landfill. And so by adding a solidifier to the canister, it doesn't have to be incinerated. It can go directly into the municipal trash. If you think about disposing things like diapers, those don't have to be incinerated at home. Another thing that we found was just a lot of things that do go into the biohazard don't necessarily need either. We found very minimal things. Only the blood-coated rags needed to be in the biohazard. Most things didn't have to go there. You can see like this is a sharps container. Most of those things are not actually needles. Those actually are just medication vials that needed to go into a medication route of disposal or a glass. And so by educating the people in the endoscopy suite, we hope to make better changes about what we can do. Thank you.
Good morning, everyone. I'm Helen Cerisi. I'm faculty in the Thayer School of Engineering, and I'm a glaciologist. Well, Hawley this morning already told you why ice sheets are interesting and fascinating. On top of that, I want to add that they're really important to understand because as they are losing mass, they're contributing to global sea level rise. And that's what I'm going to talk about. In my lab, we try to understand, simulate, and project the evolution of ice sheets so we can be better prepared for that. So most of the observations that we have about what we know about the ice sheets comes from remote sensing observations that have been acquired over the past few decades. This is some examples showing the mass loss in Antarctica. So you see the trend of Antarctica losing mass. And here looking at the spatial pattern, you see that the changes is not happening uniformly, but some regions are a lot more affected than other ones. At the same time as this is happening, we can observe how the ice is accelerating, ice fronts are retreating. And as I said, not everything is happening at the same rate everywhere. And why is that happening? Well, this is happening because ice sheets don't live isolated from the rest of the climate system. They interact with the ice, the ocean, the atmosphere, the solid earth. And so if you want to understand what's happening, we have to take that as part of our climate system. Another thing you might notice from all these observations is that they're about observing the surface of the ice or depth integrated quantities. But as soon as we try to understand what's happening below the surface, we have very few observation of glacial and basal conditions. And so that's another big part of the problem is that we cannot observe much below the surface. What I do in my lab is try to reproduce these past changes that we have observed in the past few decades to improve projections of what's going to happen in the future. And so to do that, we use numerical models. We put parameters for geometry, initial conditions, forcings from the climate system, run finite element large-scale models of continental scale, Antarctica and Greenland, and calculate ice temperature, velocity, and how these things change in time. What goes into these models are typical physical equations, mass balance, energy, stress balance, and on top of that, we also have to include parameterizations of processes that are, kind of difficult to observe here, friction, calving, and things like that. And as I said, we have observations, and so we use these observations as input parameters for the models, geometry, initial conditions, and we also use that to calibrate and validate our models. And a big part is like, how do we initialize them with these observations? What people have done so far using observations is that, we can do data assimilation. And so let's imagine here for a second that this is a curve showing the evolution of maybe velocity at the surface of the ice for one point, but we have the same for every point. We have, for the longest time, we had very few observations. We had one snapshot of velocity, and we wanted to reproduce that at the initial time, and then to capture that in our model. And so we do an optimization problem. We have this cost function. We want to minimize the distance between the observed and model velocity of the ice. We do that for the entire glacier, and then we initialize our model at this time T1, and we hope that as we run the model forward in time, we will kind of capture the trend. Reality is that inverse problems are impulse problems with not more than one solution, and so what happens more often than not is that instead of nicely following observations, the model ice sheet grows quickly or loses mass a lot more quickly than what we have. But over the past decade, we've started to acquire more and more observations, and so now we have not just one velocity map, but like a number of those, and so we can change slightly our optimization problem so that now we have this sum over time, and so we try to fit all of the observations that we have. Turns out this is a much harder challenge, and we need very automatic differentiation and heavy computational problems. But by doing that, hopefully we can better capture and stay within the observed trend. So these are some things we have. Something we've done in Qulleq Glacier in West Greenland, Northwest Greenland. You can see here, this glacier has accelerated slightly until from 1985 until 2007, and then started accelerating a lot faster. And so this figure on the right shows what happens if you initialize your model in 2007, as we used to do, and try to reproduce the acceleration after that. And we underestimate the acceleration and therefore the mass loss from this glacier, as opposed to initializing that over this, and I don't know why the gray box doesn't show, but it doesn't matter, from 85 until 2007, using over this period where it was relatively quiet and barely accelerating, and then we let it evolve after 2007 in the same way. And in that case, you can see we capture a lot better the acceleration and therefore the mass of this glacier. So that really shows that we, by using all these observations we have acquired, we can probably do a much better job at capturing these changes. That's for one glacier in West Greenland. There are more than 200 glaciers in Greenland, so I guess we have a lot of work ahead of us to scale that to much larger scale. I'm going to stop here. Thanks a lot for your attention.
All right, hey everyone, I'm Vikrant Waze. I'm an associate professor in the Third School of Engineering, and I've been at Dartmouth for over 9 years. And what we do is called as operations research, which means essentially applying math and computing tools to solving large complex system level problems and trying to optimize these systems, make them behave better. And the kinds of areas I focus on includes things like transportation, logistics, healthcare, climate, and energy. So there's a whole bunch of things that I would love to talk about, but today I decided to focus on one particular project that is in collaboration or primarily done by my PhD student who is here, Spencer. If you hang around until later today, then I will be happy to talk about some of the other things going on in our group, just to get a slightly broader picture. But right now, in the next 2.5 minutes, I want to talk about how we can use machine learning and AI to fight wildfires. So what's the problem here? We know that climate change is directly responsible for a lot of dimensional worsening of fires. So you know that the warmer climate creates dire conditions, which leads to longer wildfire seasons and more intense fires and so on. We all experienced a lot of it recently in the North America as well as Europe, in various parts of Europe. And the problem that we need to deal with is that once the fires are burning, how do we allocate our scarce available resources to mitigate these fires as quickly as possible while trying to protect the most important resources and communities and various assets we have. So in one of the recent sort of quotes, the battalion chief of the California Department of Forestry and Fire Protection said says that when computer models become important is when you start having multiple fires in a state and you are trying to allocate available resources across those various areas. So this becomes a complicated dynamic resource allocation problem, which means that the fires are burning everywhere. And what do you do? Where do you send your available resources, such as people, the firefighters, trucks and planes, and many other resources? So this is the problem that we've been focusing on with Spencer and I. And so if you look at the bottom here, there are two kinds of questions we can answer. We can answer the question of resource deployment and utilization, which means what do we do once the fires are already burning? These are technical questions answered on the horizon of few days or hours sometimes. On the other hand, on an annual level, you will want to understand how much resources are needed to fight these fires. And this is getting worse, so we need more and more resources. You can see a picture of if we do these decisions right, what we can do. We can perhaps put water or chemicals on these fires to douse them as quickly as possible while affecting as little of the communities. And so what we have been doing, what Spencer has been doing is that he's collecting a lot of geospatial fire data, vegetation data, weather data. It's a huge data project. And then we combine it with models, which to be very specific are deep reinforcement learning models to try to come up with optimized strategies for fighting these wildfires, the real wildfires. And so hopefully I can show you a picture here, a video here where we are trying to put these barriers in place. The barriers are the parts of land where the fire cannot cross it because we have removed all the fuel from there by one reason or the other. So there is a video. Okay, so the fire spreads, we start stopping it, and then we are partly successful. The areas on that side are protected, areas on this side are not protected. So these are the kinds of things that we can look into with real data and try to provide help to the decision makers about how we can do it. You can see here that these are very large and sized models and computing methods for computation that are efficient in terms of how quickly they can solve the problem and how little space they need. They are very important. So that's where a lot of the research focus is. This is ongoing research, so this is not done. But here's a flavor of what sort of things we can do out of this work. We can try to look at things such as aircraft speed. We can look or truck speed or number of people we have, or we can look at how much is the available capacity of the tank of the aircraft, so how big or small the aircraft is. We can look at these kinds of things and try to understand the effects of those things. in terms of how quickly we can douse the fire and how much can we protect our community. So you can imagine the extent of where we can go with this is we can look at resource allocation decisions and try to allocate budgets for the right amount of firefighting resources that people need over the longer run. So thank you very much.
Yes.
Okay, thank you very much. Good morning. Yeah, you don't see my name anywhere, so please remember my face. Take off my cover to save the time. My name is Chen. I'm a professor of geography, and this is the title. I want to give an overview of this topic and some specific work we have been doing. Generally, we can recognize two types of impacts of climate change on health. The first is on one end, it's the increase of frequency and degree of extreme weather, and at the short term, and the impact will be local and directly impact on human bodies and mostly respiratory and cardiovascular diseases. So this is on one end of the impact. On the other spectrum of the spectrum of the impact is kind of a long term. It's the change of general climate conditions. It's not just a temporary extreme weather, but a kind of long-term change of the climate conditions, including the long-term and the region. The scale is a long-term and the regional and even global impact. So both spatial and temporal scale is large. And this impact kind of indirect, not directly on human body, but kind of indirect through the impact on ecological system. And a typical example is backbone diseases, the emerging and re-emerging and expansion of backbone diseases become a pretty significant problem. And here is one example is the dengue fever. And this is a map of the spread and the current situation of dengue fever. This is the most prevailing infectious disease currently in the world. And according to WHO, there's some really significant impact. And because of the climate change, because this is a mosquito spread disease, and the mosquito highly depends on the ecological conditions. The impact is habitats because of the change of the temperature and the precipitation. Another example is malaria, and there's a situation of malaria. I'm not going to really go through read numbers, but another very significant and global issue is backbone disease. This is what the project we have been working on, the Lyme disease, and this is a spread of Lyme disease, and that's the ticks. The Lyme disease is a tick-borne disease spread by ticks, and the situation of this particular ticks in both the eastern half of the country, that's kind of a tick species, and then the other one is on the west. This is another tick species that can spread Lyme disease, and it's a situation, a spatial distribution of these tick species. And this is situation dynamics of Lyme disease in this country. From this 1996 situation, this is 1940. This is not updated. Current situation is, of course, is more serious than this. This is a project we have been working on. It's sponsored by NSF, and it's kind of a nationwide study of the Lyme disease spread of Lyme disease under the climate change. Okay, this is New Hampshire, and in this project, our Dartmouth team study areas New Hampshire, and these data, public data published by New Hampshire EHS. This is publicly available data for a 5-year time period, 2005 to 2009, that's 2010 to 2014. And you can see the situation, you can see the change. The color are comparable. You use the consistent legend. So these colors comparable, so you can see the change, the dynamic of the situation of the Lyme disease. Our approach, because I'm from geography, my specialty is the GIS. So what is GIS? If you heard of this, then this is something you're familiar with. If this first time you here there's an acronym, that's GIS, a Geographical Information System. So basically it's a computerized system to collect and process and compile geographic information and run spatial analysis, run spatial statistical analysis to deal with situations. And this has become a very important approach to epidemiological studies, to public health studies, and the Margaret and Celia studies we have been working together. Okay, this is the kind of a description of GIS. And anyway, this kind of study is highly interdisciplinary area, including biomedical sciences, entomology, epidemiology, ecology, environmental science, climatology, social science, data science, math, computer, game, AI, and GIS. So they're highly interdisciplinary and are highly welcome any discussion for collaboration and seeking opportunities for that. Okay, and our overarching goal from our perspective is predicting the spatial temporal dynamics of the disease under the climate and environmental changes. Okay, thank you very much.
First, Palatinski.
Hello, good morning. I'm Chris Polaczewski. I'm actually a cryosphere researcher. This is not my slide. There we go. I'm actually a cryosphere researcher. I work on sea ice, albedo feedbacks, the mechanics of sea ice and things like that in the Arctic, and that is not what I'm going to talk about today. I've worked on that for a while. I can tell you sea ice is going to go away in my lifetime. I've emitted around 100,000 tons of carbon studying the sea ice and all the work that I've done up north, and perhaps that's not all that productive anymore. I don't think we really need as much detail on the sea ice as we're working on. I'll still work on that too, but in my extracurricular activities, working on a little bit of something different here. For those of you who know me, you know that I'm lucky enough to be married to a farmer. My wife, Nora Lake, runs Sweetland Farm in Norwich, Vermont. And we have made a pledge to get off the juice, 90% reduction of fossil carbon in the 10-year period. We made the pledge in 2018, so we're now 5 years into the pledge. We've done all the easy stuff. We've got solar panels up, we've super insulated our buildings, we've changed out light bulbs to LEDs, gas irrigation pumps to electric, all stuff that honestly you all should be doing in your homes and lives as well. That's all done. We got some fun help from students. Tuck students have been involved in working on managing our employees to reduce the number of trips around the farm with fossil powered equipment. We've had a Thayer group design this affordable housing unit, it's a net zero unit for our crew to live in. We've had some involvement from earth sciences folks in our silvicultural programs and start carbon sequestration in our forests. So lots of opportunities for students and research activities. And now we're starting to transition into the hard stuff. We are now 63% down in carbon emissions from our 2018 baseline. We're now producing a CSA share worth of vegetables. That's a week of vegetables every week for 24 weeks of the summer on 1 gallon of fossil fuels emitted per year. But we said 90%, we're only 63% down. So a bunch of R&D type stuff is actually happening at the farm now. We have about $2 million in research grants to produce a biomass boiler system to heat our greenhouses. We went with biomass for the greenhouses because it does not align with the curve of when electricity from solar panels would be available. It's a midwinter load and it happens in the coldest nights of the year. And by the way, if the power goes out, we're really screwed because the plants get frozen. So we wanted to have something that stores better, but you all know there's some controversy with biomass at this point, whether it really is carbon neutral. So our burner is going to burn waste products. Green wet wood chips will be taken in and dried. Lawn clippings will be taken in and dried. And we also have a whole bunch of pollution controls we're working on, cyclones and electrostatic precipitators to try and make it comply with Vermont's stringent PM 2.5 regulations. Different project, we've got a grant, the first large horsepower electric tractor in the state of Vermont will be at the farm this fall. A whole bunch of work to electrify the implements that we have to go work with that tractor. Also, another grant pending that I'm hoping we're going to get for a student group to work on electrifying an existing tractor. We've got some projects working on removing invasive species and replanting keystone species like chestnuts, blight-resistant chestnuts on hillsides, and studying the carbon impacts of those changes over the next 20 years. And we've got some SARI grants working on life cycle analysis of choices that we make. We are not certified organic, but we do pretty much everything you would do certified organic, except once in a while we want to think about whether the organic practices are best. And so one of the examples of that is in nutrients on the farm. Phosphorus and potassium all come from mines ultimately in the ground. You may run it through a cow first and bring it to your farm as manure and call that organic then, but ultimately the minerals came from the same source. Okay, so which of those is better? I don't think we've really done a good job of thinking about that. The manure is heavy, it uses a lot of diesel fuel to haul it around. I actually don't know the answer to this question, that's why we have a SARI grant to work on it. But we're going to start trying to ask questions like that about how we can improve our practices by really thinking it through and quantifying things. There are tons of opportunities for plenty of people to be involved out at the farm. The permitting process is great. I asked Nora and she approves it. So come on out and get involved in actual research that has a very short timeline between when you think about something and when it actually gets implemented. And look forward to working with you. 3 minutes, thanks.
Jesu.
Yes.
Thank you. Hello, everyone. So I'm Joshua. I'm from there. I'm a research associate from Professor John Desk Group. So unfortunately, I forgot my name. It's reminder from Professor Sheet. So if you're interested in my research data, please mark my name in a new fresh handout. So today I want to talk about my research about advanced function materials for powering biomedical device. So in modern healthcare, we use lots of medical devices to either support, enhance, or replace or fraction of the whole biological structure, that like this cochlear implants. But unfortunately, or not, I mean, they have one more problem. But technically, it's not a problem because they are all run on the battery. This means over the time, they have to recharge or replace their battery. So for our research, we kind of focus on one specific one called cardiac pacemakers. So this little device has two key components. One is the small battery pack and with a small computer inside, and also has one or two leads that really go inside of the hearts. So, and all the time, the patient needs to replace the battery through surgery every 5 to 7 years. But unfortunately, the people who need that device become younger and younger. So all the time, they have to replace their surgery multiple times. So definitely, it's going to suffer a high rate of infection, not to mention high medical bills and also low life quality. So how can we tackle this problem? So after communicate with our clinical collaborators, we realized that actually our heart is a very powerful engine. It can generate about 1.4 watts of power, but in comparison, the pacemaker can only use microwatts level power to operate. So if that means if we can harvest a fraction of the energy, we can significantly prolong its life. So how we do that? So this is a video. This is the lead. This is for our animal test. This is the lead actually implanted into the pig's heart. You can see the lead has a significant motion there. So and then we use the special materials called piezo materials to convert this spinning motion into electricities. So and then here, this is the one of our research we call the Karagas device. So here for this research, our device we use actually porous piezo thin film, which has high energy conversion efficiency. And then for this thin film device, we introduce this cutting pattern. We call it Karagas pattern. So the advantage is, so this pattern can help us wrap the device on the lead and also without compromising the cardiac motion. So it's very important for human beings. So, and all the years, we have done also work on this, and our work recognized by both industrial and academia. As you can see, all these cover images from our publication. And also we engage with industrial collaborators to drive our research forward. And I think for now, it's fair to say the batteries still play a very important role in this field. But I think in the future, it will be nice to have a device like this does not require battery and also lightweighted, and even smaller size compared to commercial products. So the patient in the future won't worry about battery changing for their rest of life. Okay, thank you.
Let's be the rapid fire.
I have to follow when you went under time. I'm Rafe, I'm an instructional assistant professor at Thayer, and this is a pitch for you all to consider including a design thinking project within your course and programs of study. So first, what is design thinking? Well, design thinking, there are lots of different design disciplines like architecture, graphic design, interaction design, experience design, engineering design, fashion design, et cetera, et cetera. And design thinking is what makes all of these things design. And then how might we leverage the processes, mindsets, skills, tools, and techniques from design disciplines into problems that don't fit neatly within one of those design fields. So the big question is in design thinking is how might we bring design expertise to bear on challenges that go between and beyond design disciplines. So a couple examples of projects and classes at the two former institutions that I taught at. One was at Princeton, and in this class, we worked with a municipality to redesign the climate action planning process. In 2009, they released a 176-page climate action plan. A lot of brilliant thoughts went into it, no one read it. And so the challenge in that class was, how could we redesign it? And the student team ended up coming up with an inchworm approach, where in 2019, the municipality released their climate action plan 1 month at a time with a whole suite of events and communication strategies around each part of the climate action plan. I then taught at Tulane, and one of the courses I co-taught was a special topics course on climate change. And one of the student teams worked on reimagining climate change science integrated into every introductory course across any major at Tulane. So there's a little bit of implementation there, but the question there was how could every student, regardless of their major at Tulane, gain sustainability fluency, which was one of the big initiatives of a liberal arts education. Some reflections on lots of different design thinking projects that I've been involved with in courses is I often find that the most important things students learn are rarely planned. I love learning objectives, but I think there's so much hubris when we develop learning objectives that like if students learn everything in our courses, climate change will be tackled, and I don't think that's true. So one of the questions that I'm asking across courses is how might our curricula themselves be experiments that help us learn what we need to teach and sort of being part of the innovation process as we think about needing the solutions that are needed in the future. So here's the pitch. Design thinking project in your class or curriculum. We actually have a grant program with DCAL to help any instructor at Dartmouth reimagine one of the units in the course as a design thinking project. What that looks like in practice is students going from observing, this is called cycle for learning, observing what exists now in the bottom left corner, sense making about what exists, so that's kind of like science, then articulating principles for how the world could be different, that's abstract synthesis, and then finally creating real artifacts to try to change the world in the way that it is, and then hopefully being cyclical as well too. So the grant has both financial support as well as interpersonal support. And I really believe that the grant and integrating design thinking does not take away from the existing learning objectives in your course, but helps deepen them through engagement while also bringing in many of the wonderful learning objectives from design disciplines such as interpersonal skills, creativity, et cetera. So if you're interested in that, you can get in touch. Thanks.
Hi folks, I'm Eric Osterberg, and there'll be a little bit of parallel with Chris's talk we just heard.
in that I was hired by the Earth Science Department back in 2012 to study climate change, primarily using ice cores, but that's not what I'm going to talk about today. I'm going to talk about what I've been doing basically in my extracurricular time and my volunteer time, which is trying to help our local communities in the Upper Valley here become more resilient to climate change through an organization called the Upper Valley Adaptation Work Group. And we've been around long enough that you notice climate is not in our name. Because when we started in 2012, we couldn't have climate in the name because you instantly turn off a whole bunch of people in the community. So things have come a long way. Our mission statement is to help build climate resilient communities in the Upper Valley through research, information sharing, and education. And so who we are is basically a group of people across the different sectors in the Upper Valley. So obviously academics like myself, people in the medical sector, but people in the surrounding towns, regional groups like our regional planning commissions, who their job in both sides of the river, Vermont and New Hampshire, is to work with the towns to do all sorts of good stuff. State agencies in both New Hampshire and Vermont, nonprofit groups like Vital Communities, businesses like Hypertherm, who's a real leader in our local business community here on becoming more resilient and also reducing their carbon footprint and so on. And so most of the people who are involved in this are also, they have other jobs and they're doing it in their volunteer time too. But what's really neat is that this work is taking up more and more and more of our respective lives. We're spending more and more of our time dedicated to it, and things are evolving quickly. So we do a lot of things. We started off basically doing information sessions, public forums, where maybe 100 people show up on a particular topic like floods and droughts, for example, just trying to raise awareness about climate impacts here in the area and how you can become more resilient. Then back in 2018, we started something called the Climate Change Leadership Academy to try and basically take people who are really enthusiastic about climate and wanted to do something and help them to do something, help them to do some grassroots project in the local community to help make it more resilient. So if you would like to interact with folks who are trying to do this kind of work, maybe through your research, you have some projects that would be helpful for really enthusiastic people of all ages and walks of life to work on, this could be one way that you could do it. You can talk to me about that. The other thing that I've found is that my research world here in Dartmouth is converging into this work. So NSF, other funding agencies increasingly want scientists like us, or at least like me, to work directly with stakeholders in order to actually come up with your research questions, right? Co-developed research questions. So you don't go in saying, oh, I know exactly what I need to study, and then we report out to you at some point in the future, but you work with folks from the ground level throughout the project and co-develop this knowledge. This is the kind of thing that Mary Albert's doing in Qulleq. We're trying to do it here in the local community. And so one example of this, we got a small seed grant for 1 year from NOAA to look at the issue of climate migration. And we worked with communities across northern New England, all the way from upstate New York to the coast of Maine, to talk about this issue and hear their thoughts. And basically people weren't worried about climate migration. What they were really worried about is housing, 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 housing. That's what we kept hearing about. We don't have enough housing. The housing isn't resilient. The housing has too much carbon emissions. The housing is unjust. And so we're now turning this around into a $5 million cap RISA grant proposal, at least, to really focus on how do you build climate resilient, equitable, just housing in northern rural communities. So listening to people and then figuring out what is it that they actually want and need and doing the research that way. So more and more of my work is actually with this. It's not just my volunteer work anymore. This is now more and more of my Dartmouth work. And so you as researchers, if you want to start working directly with stakeholders, at least here in the Upper Valley, come talk to me. We've been working with these communities for 10, 12 years now. We've developed a lot of good relationships. They know us, they trust us, and we can help you be a bridge to these community members. So I'll leave it at that.
America.
Okay, good morning. My name is Catherine Marika, and I'm an associate professor of chemistry at Dartmouth College. My group in the chemistry department specializes in porous multifunctional materials for healthcare and protection. And specifically today, I'm going to talk about some self-assembled materials that can be put onto textiles to provide chemical detection, filtration, and detoxification all at the same time. So these materials that we work with are known as metal organic frameworks. This is this material here. And this material can be self-assembled. So you can think of it as kind of like Lego building blocks, putting themselves together in solution phase. There are organic components, these basically molecules in gray, and then metallic components that come together and make a material that's capable of interacting with its chemical environment and changing its properties, such as conductivity. And by putting these kinds of materials onto textiles, we can create a porous, multifunctional composite through the process of self-assembly. So the material puts itself into a textile, and this textile becomes multifunctional and capable of sensing filtration and detoxification. And we really see this as a platform technology that can enable detection of toxic gases, neurochemicals, and ions. And some of the toxic gases that we're focusing on are hydrogen sulfide and nitrogen oxide. So these are toxic products of combustion. They're products of forest fires. And what we're looking to create is potentially personal protective equipment that could protect firefighters or coal miners from exposure to these toxic chemicals. And these textile composites with the porous framework materials are really well suited for this kind of application because they're extremely robust and can withstand tests of abrasion, ironing, and laundering. And even when we wash this textile with detergent, peroxide, and bleach, its function is retained, and its function is sensing filtration and detoxification after multiple washing cycles. So overall, we think that these multifunctional materials can offer a new electronic textile sensing and personal protection technology with potential applications in healthcare, personal protective equipment, and some potential for global scalability. Thank you.
Alicia Garrison.
Hi, my name is Alicia Garrison. I'm an assistant professor in the Department of English. I'm going to sort of take us from the empirical to the narrative and thinking about the way that poetics in some way acts as a kind of supplement to thinking about questions of energy and climate and the geological turn that we're now calling the Anthropocene. I prepared some remarks to be a bit more efficient. The coast is an intimacy where the rocky shore meets sea, but it is also an index of human and planetary histories, sedimented with multiple generations of socio-political and geophysical systems. My work interrogates the Anthropocene as a historical and literary, as well as geological category of complex ontologies and intersecting timescales to read how literary descriptions of Irish coasts are shaped by colonialism and revolution in the longue durée of anthropogenic warming accelerated by English colonial conquest. Set in the wild west coast of Connaught in the 18th century, The Wild Irish Girl was published in 1806 and gave rise to the historical novel of the national tale, genres developed in Ireland primarily by women writers. Proto-feminist Jacobin novelist Sidney Owenson was one of the first professional women writers in Ireland who took the name Lady Morgan in 1809. Born repeatedly on the Irish Sea to an Irish Catholic father and an English Protestant mother, Owenson was author of 4 highly successful Irish novels that shape Irish nationalism after the Act of Union. Owenson's feminized literary history has much to say about historical developments in the wake of the United Irish Rebellion and the Act of Union with Britain in 1802. And her political radicalism helps invent the proto-modernism of the Irish novel. But these histories are made much more complex by the novel's depiction of Irish coasts, which demand rich interdisciplinary inquiry into the turbulent history of Irish seas on shores where socio-political histories of colonial extraction meet natural history and a changing climate. What a picture, the narrator exclaims when he arrives on the wild west coast of Ireland at the ruins of Innismore Castle hanging on a cliff between mountain and vale, and the swelling of the ocean. The coastal air plays a harp's melancholy vibrations gently and autonomously but a contrary wind springs up. The wild Irish girl's interest in what the air carries, what it exhales, and how wind, breath, and voice resonate on the coast of the northwest of Ireland, what the novel calls the wildest shores of the greatest ocean in the universe, stretches our understanding of historical form to include non-human life. My work follows the elemental turn in Anthropocene reading to provide a microhistory of air on the coast and what the air carries, forcings of wind, vapors, and vibrations. What I call coastal sense transports us beyond the bounds of the human to understand contradictions between air that carries Irish national sentiment in voice, breath, and sound, while also indexing rising atmospheric carbon, forced evictions and enclosures of land, erratic stormy weather, tying the Anthropocene to the turbulent seas and stormy winds of English colonial conquest. We look to the literature of the Irish coast to read not only violent crossings of the colonizer, but also the energies of rebel Irish, their French allies, and the wind and the sea itself, which fight for air. Owenson's Wild Irish Girl begins with the splendid spectacle of the Bay of Dublin, which you see here, a scene of picturesque creation for foreign investors arriving by boat to Dublin Harbor. After the Cromwellian settlements of the 17th century and through the long 18th century, history and literature describes the exploitation of Irish environments as land improvements. Plantations, drainage, deforestation, mining, steam, road and canal building, land surveying, renaming of Irish places, natural history inventories, weather records, and more, all in the service of Protestant landlords to conquer and order an unwieldy environment, conflated with the Irish Breton laws, chieftains, and rebels. In the 18th century, descriptive tours and landscape painting represent the Bay of Dublin as calm and tranquil, serving as an advertisement for this language of improvement with shifts in land ownership from Catholic proprietors to would-be English Protestant planters. You can see that other representations run contrary to this dominant representation and represent the seas as quite stormy, reflecting the sort of political and revolutionary history of the time. While many critics have written about human and colonial revolutionary history in Wild Irish Girl toward the development of Irish nationalism post-Union, the novel's representation of shifts of climate, aspects of weather, and movements of air, sound vibrations, and water, particularly on the Irish coast, have been overlooked. Owenson's novel shows how the Irish coast is not merely a picturesque visual aesthetic fixed in a painterly frame to appeal to prospective planters or gaze at through a window by travel writers, but a moving complexity and entangled relay of intersecting ecologies and weather patterns. Thank you.
There we go.
Hi, everyone. My name is Jerry De Silva. I'm a professor of anthropology. That is not me. I feel certainly that way since I became chair of my department. What I want to, I'm an anthropologist. I study fossils of early human ancestors to try to reconstruct why we are the way we are today. I work mostly in East and South Africa, and my lab does a lot of work on anatomical reconstructions and behavioral reconstructions of our ancestors. And what I want to sort of argue is that energy extraction and landscape modification is nothing new. That we've been doing this for a long time, and this has been critical for our survival. What is new is the scale and the impact. So all living organisms extract energy from their environment. Apes are particularly good at this, and they'll use technology to extract, say, termites from a mound like you see here. They'll even make hunting sticks to hunt small mammals called bush babies. And most likely the common ancestor we shared with chimpanzees 7 million years ago was also using technology to extract resources from its environment. Now there's a game changer that happens around 3.5 million years ago where we start using stone in order to make our technology. This happens with predecessors of genus Homo, what we call Australopithecus, like the famous Lucy. And then by 2 million years ago, we get really good at it and we start going specifically to quarries with certain rocks that have certain material properties to get those stones to make our tools, that have the sharp edges to cut meat from bone, to cut plant material, and to dig for tubers. Now, this technology helped unleash new energy sources that helped fuel our growing brain. And this led to a feedback loop where the enlarged brain led to better technology, which led to more resources, which led to a growing brain. And off we went through the Pleistocene. Now, before Homo sapiens even evolved, our ancestors were modifying their landscapes to help solve ecological challenges and inconveniences. This is a discovery that you may have seen in the news. It just came out last month of trees that had been deliberately felled 500,000 years ago by predecessors of Homo sapiens, most likely Homo erectus, in order to construct a boardwalk over a wetland, or even to make a wall of a shelter. It's not clear what the use was, but these trees were deliberately felled and interlocked together to make a structure. This is 500,000 years ago that this is happening. There's another site in Germany where trees were felled to make wooden hunting sticks as well. And so cutting down trees is nothing new. 250,000 years ago, at a site in Germany called Neumarkt Nord, Neanderthals, our European cousins, Neanderthals, moved into a region that was forested, and using fire and tools, they cut down the trees and established a new landscape that was more grassland environment that they inhabited for millennia until they eventually left the area and it grew back into a forest. So this is the oldest evidence, 250,000 years, of large-scale landscape modification by ancient humans. Now, what about fossil fuels? Well, it appears that our Neanderthal cousins discovered that too. This is a site in France where Neanderthals were extracting from an area that was about 5 to 10 miles away, lignite or brown coal that they were bringing back to their hearth and adding to the fire for fuel. Now, today, 300 million tons of brown coal is burned in Europe, where Neanderthals first began this practice 70,000 years ago. So humans are really, really good at extracting energy and altering their environment. And I think we always have been. And this is the legacy that we've inherited biologically and culturally as we confront the challenges we now face, thanks to the unrelentless application of energy extraction abilities that have ancient roots and allowed our ancestors to eke by in an ancient and unforgiving world. Thanks.
Carol Anderson.
Hi, everyone. I'm Cheryl Anderson. I'm a general pediatrician at Dartmouth. And I'm going to be talking to you today about climate-informed care in pediatric practice. So I'm fortunate enough to be part of a team who's awarded a one-year Irving Seed Grant focused on climate-informed care in the pediatric primary care office. And as you've heard already today, we know that climate change is already posing threats to human health and that children are uniquely vulnerable to these effects. And children from disadvantaged populations are at even greater risk. So the American Academy of Pediatrics was the first organization to publish a policy statement on the health effects of climate change in 2007. In 2015, it published a revised statement suggesting that pediatricians use the existing anticipatory guidance as a framework for discussing climate change with families. Each primary care visit offers a unique opportunity to screen for social and environmental determinants of health and allows for the promotion of healthy behaviors. But despite this, climate is not a routine part of our anticipatory guidance, and few pediatricians have had formal training on the topic. So our project aims to develop, launch, and test a model of practice-based training and systems change within all 7 Dartmouth Health pediatric primary care practices. We're going to do that by developing a climate-informed toolkit and conducting practice-based trainings. And then hopefully we will propose suggested ideas for incorporating climate and health into the pediatric residency curriculum and medical school curriculum. And thank you to my team members, several of whom are here today and also presented. So this is currently a work in progress, but we did an initial survey to providers assessing knowledge base, comfort level, and barriers to incorporating this guidance into their existing workflow. And we also did structured interviews with 16 individuals across the 7 Dartmouth Health practices. And what we found is that 88% feel that climate change is a concern, but only 50% feel comfortable discussing it. And the top challenge is time. 96% of respondents felt that adding another conversation to our already busy visits would present at least a little bit of a challenge. So this was followed by concerns over the politicized nature of climate change and access to resources and knowledge on the topic. So what we've determined is the intervention needs to be focused and use existing workflow and be adaptable to the patient's needs. And here are some of the examples of what's going into our toolkit. We are currently building a toolkit with activity game books for young children, pediatrician and provider and parent brochures, and posters for the waiting room. And in work in progress is scripts for role-playing videos for working this into a busy practice. So we'll measure the effect of our intervention by post-training surveys, parent surveys, and searchable fields within the EMR. And again, just like to take a moment to thank my team as well as our colleagues at CPDE for helping us to implement our survey and the interviews. Here's some references.
You're ready.
Good morning, everyone. Good to see you. As announced, I'm Lee Lind. I'm a professor at Thayer School. I lead the Energy Engineering Program area and also an adjunct professor in biology. And so, very busy slide. The point of this is that there are lots of things one needs to consider when thinking about sustainable biofuel supply chains. They need to be cost efficient, carbon efficient, land efficient, demand responsive, poverty and development responsive, entrepreneurially successful, and they need to have a philosophical framing. And it's important to think about being both hubs and spokes on wheels. And so there are a number of efforts across this spectrum. I lead with a whole group of collaborators. There's 21 collaborating institutions. I've been doing this my whole career, 11 of which are international. So we are broadly engaged. You can read about any little thing there that attracts your interest, but I'm going to keep going in the interest of time. So just a couple of things. We're honored to have a seed grant from the Irving Institute. We've submitted an invited paper to Nature Communications, which includes the following sentence. These observations support but do not prove the hypothesis that a food fuel win-win is possible wherein large amounts of liquid biofuel feedstock are obtained from land dedicated to food and feed production while not sacrificing soil organic carbon and improving the economics and sustainability of annual crop agriculture. So we'll see what the reviewers think of that. We also have a collaborative project with Caitlin Hicks-Prees in biology, looking at providing experimental evidence for that hypothesis. This graph on your left is not mine. It's by my friend Pete Smith at the University of Aberdeen, who is a global leader in thinking about nature-based carbon removal alternatives. And the number of axes here, water use, land requirements, energy required, et cetera. But you see the big three when it comes to negative emissions. That is CO2 removal, which we certainly need to do, our bioenergy with carbon capture and storage, afforestation, and direct air capture, way above the 3 times higher than the other ones listed here, according to this study. I just point out that at this particular scale, which is only one scale, bioenergy would produce 160 exajoules. Direct air capture would actually require 160 exajoules. That's about a quarter of the total energy that humanity uses. And then on your right, yes, is a cover art from a paper from my group with a graduate student, Matt Kubis, where we emphasized, and this is not widely realized, that there are 2 climate benefits from producing biofuels. One of those is the fossil fuels you don't burn, the displaced emissions, and the other is the opportunity that biomass refining gives you for carbon capture at the point of production. The second one is larger per hectare, larger per ton, and more distinctive than the first, although the field has focused almost exclusively on the first. So in my view, the reason that bioenergy right now is a very prominent component of IPC scenarios, and the reason it will continue to be, is not primarily carbon displacement, it's carbon capture. And last, let's see, we want to go forward. Yeah, so just to elaborate on that theme a little bit, this is one of many scenarios. It's the 2-degree scenario of the International Energy Agency. And in round numbers in 2075, which is a hell of a long way off, about half of transportation globally is provided by electricity and hydrogen with roughly 0 emissions, and half by biofuels. And so you can calculate the displaced emissions from 50 exajoules of biofuels. It's about 3.4 gigatons of CO2. And relative to what we need, that's a lot. It's about 11% of what we need. By contrast, if you calculate negative emissions, it's about a third of what we need across all sectors, just underscoring the importance of the carbon removal. Sorry to go over time. Thank you.
Last speaker of the session is Jessica Sana, and we'll take a 10-minute break afterwards. We'll be back here at 11. Give it over to Jessica.
Thanks. Hi, everybody. Oh, can you hear me? Is this working? Yeah, hi, my name is Jesse Kasana. I'm a professor of archaeology in the Department of Anthropology. And I have to advance this. Here we go. Oh yeah, right, great. Anyway, a lot of my research lately has to do with trying to reconstruct ancient systems of agriculture and other forms of land use in the distant past. These are preserved in a dizzying number of ways all over the world, from raised beds to terraces to water management features and all kinds of other stuff. These are just some of our recent field projects. These things are extend over vast areas of the landscape. They they are often kind of hard to see on the ground and difficult to preserve and protect because most people don't really notice them or care about them very much, but they're actually extremely valuable. They tell us a lot about where people were farming, what they were growing, how intensively, when they were doing this. And therefore, they tell us a lot about people's interactions with the environment, the sustainability of past agricultural systems in light of changing climate, and lots of other really important issues like this. So our research team at my lab, the Spatial Archaeometry Lab, as we call it, or Sparkle here at Dartmouth, devotes a lot of our efforts to the development of new remote sensing technologies that are a key tool that we use to try to discover and document these kinds of features. These slides come from one of our recent projects at Picary's Pueblo in northern New Mexico, where we've been working in collaboration with the tribal community to try to document the extensive remains of these long linear stone walls that cover many square kilometers of the Pueblo, the reservation, and surrounding federal lands. These are the remains of a gigantic agricultural system of terraces and field walls and canals that used to exist in this area that today is covered by a dense pinyon juniper forest, but in the past would have supported a huge agricultural enterprise that sustained a very large population from about 1200 to 1500 AD. So today these things are often hidden throughout the forest, and they're very difficult to see. They're also under imminent threat from destruction from a large solar farm that's actually being built right here on this same spot. So what we did is we went out there over the past 2 summers and deployed a new drone-deployed LiDAR system. This is a laser that shoots down and allows us to see below the trees and try to map these features. These results have been really successful. The LiDAR imagery that we generate allows us to see through the trees and other vegetation and filter that out, revealing what we call a bare earth model. That's like a topographic model of the land without all the trees and junk on top of it that we don't want to see. And what it reveals is this unbelievable number of terraces. This is all these linear features stretched all across these hillsides, all over the Pueblo. Also lots of other ancient building remains and ritual sites. So collectively, these kind of new data are really reshaping what we know of the agricultural and land use history in the Highland Southwest, and showing that today these areas of the upland plateau were once clear cut of trees and intensively farmed, supporting a huge farming operation prior to the arrival of Spanish colonists. This is just one thing, many parts of the world where we're doing this kind of work. It's exciting new stuff, and so thank you very much.
All right, we will meet back here at 11:25 for the Sixers. Just to give you a back, maybe All right.
Yeah.
All right, and everybody, is outside, hopefully they'll come in. We have two panels next. One is on modeling, predicting, and forecasting. Demetrius Tsanakis is going to be the MC. The way this is gonna work, each one of these panelists has 2 to 3 minutes to give an overview of what they work on. And then we open it up to the floor to ask questions and hopefully receive more answers, more details, and discussion of it. So I'm gonna give it over to Demetrius. Oh, you have it. Just want to share.
Welcome everyone to our panel.
You can give you a microphone.
Welcome everyone to our panel on modeling, predicting, and forecasting. It's a pleasure to welcome 5 distinguished panelists, all of whom are affiliated with the Thayer School. We have Professor Klaus Keller, who works on climate risk analysis and decision-making, risk management. Colin Meyer, who works on geophysical fluid dynamics and glaciology. Yes. Oh, I'm sorry. Professor Erin Mayfield, he works on sustainable systems and decision making. Professor Sarah Ellen Hersey, working in glaciology and glacial ice sheet dynamics. And last but not least, Professor Vikram Vaid, I hope I'm pronouncing it at least somewhat correctly, who works on logistics, transportation, and gains here. So, so since the time is short, I would like to give our finalists back. So please take 3 minutes.
Okay, test, yes. Research my group works in climate management, and what you see a picture here is New Orleans, where there was a climate modulated event. And the question is, how do you manage risks like this? And when you think about this, it turns out this is a really complex system. And this is a cartoon I will not really discuss in great detail, but the point is that we have complex systems that include geophysical systems, engineered systems, human systems, and human decisions. And there are positive and negative feedbacks that can lead to rather nasty tipping point responses. And the question is, how do we manage those risks? And risks management is about the future, and future is about prediction. And the question is, how do you predict? And it turned out that this is more complex because the classical way we in academia typically teach prediction is like the yellow one. You have prior knowledge, system model, line of evidence, you have some kind of data model fusion approach, box your uncle, you have a prediction. The problem with this is that the issue we're facing is one about the coupledness of human system, and humans are driving climate change, humans are reacting to climate change. And so the outcomes are compared to values, the values involve metrics, and the discrepancy then in some sort of decision making impacts the decided strategies that are folding back into the system model. So if you make predictions about a coupled human system keeping humans constant, then you have a problem because you assume the dumb farmer is sitting on your hands, nothing happens, and you do not account for the key characteristics. So this was slide number 2, and the key is that too much detail would be actually taking away the thunder from the students and the postdocs at Adam and Prabat. Please wave. They're going to give a little tour today if you're part of the lab tour, and you can ask them because they are actually the ones who make the magic happen for the paper. So ask me for the high-level bullshit and ask them for the things that actually matter. And after the least, here's a QR code and you can touch base. Thank you.
Hi, I am Erin Mayfield. I'm an assistant professor in the Thayer School of Engineering, and I lead the Sustainable Transitions Lab. Our lab focuses on 3 interacting research themes. The first is energy systems modeling and infrastructure planning. So we model how, at a macro scale, the energy system can transition in the context of climate change, and then feed that down to the micro scale, and how do we actually deploy infrastructure like heat pumps and solar.
The second research theme is developing models to evaluate social equity, environmental impacts such as air quality and water quality, and socioeconomic impacts like labor effects. And the third research theme is stakeholder planning and policy processes. So we engage stakeholders in our modeling processes and also include stakeholder values within our models as well. So this is an example of energy system modeling and infrastructure planning, looking at utility scale solar and wind and transmission build out over the long term. So this is a snapshot of our infrastructure system in 2020. So transmission are all the lines in white. Utility scale solar is barely visible, it's in orange, and then wind is in blue. And this is a snapshot in 2020. This is a snapshot in 2050. If we meet a net zero target and 80% of our energy is supplied through renewables. So when we build these algorithms, we not only account for costs, we also account for other non-cost factors that influence our decisions, acknowledging that kind of in the real world, all of these factors will influence if and how we can deploy infrastructure. So thinking about things like air quality, labor, and politics. Oops, sorry. And with that, I'll end there. I can't describe.
Hello, everyone. This is me, Myron, and I'm an assistant professor in Thayer, and I study snow and ice processes. I focus on melting and solidification, right? So if we think about glaciers, as you can see, Antarctica in the upper left, as climate changes, there's going to be a lot more melting in Antarctica. So if we study those processes from a fundamental level, we can understand how these fast flowing features like ice streams, this pointer doesn't work, but you can see that there are fast places. If you look, what's plotted is the horizontal speed. And there are places that look like little fingers that are going much faster than the average velocity, which is sort of yellow. I study melting and freezing at the base of glaciers. You can see in the bottom left. So that's a picture of Taylor Glacier. And then underneath it, there are these sort of laminated sediments, which are frozen to the bottom of the glacier, and then regular sediments below that. I also look at snow in alpine contexts. Here's some dyed water that's percolating through the snow. What you can see is that it doesn't just enter the snow uniformly everywhere, but it sort of moves through as fingers or as paint drips. And then I also think about these sorts of things in the outer solar system. So these are icy satellites. This is the moon Enceladus of Saturn, showing these regions of high localized heat on the South Pole. So melting and freezing in the context, in many contexts, from here and there. So this is just a quick overview of two ideas. On the left, this is that paint drip idea, thinking about how does the meltwater actually infiltrate in, and how heterogeneous is that? And does that matter on the climate scale? Or, we're thinking about, this is sort of a meter from here to there. So we're talking about sub-meter scale fingers of meltwater infiltrating. Does that matter to a climate model? Does that matter to a glacier process model? We're trying to figure that out. And on the right, the similar sort of thing, this is a pack of sea ice where we're modeling the brine channels. So as you have convection within sea ice because of heavier salt being rejected internally, it forms these locations where that salt is going to drain, and those are called brine channels. And those are shown as high porosity regions here on the right. And those are on the sort of meter scale. So we're using these sort of high resolution, high fidelity, small scale physics models to understand evolution of the thermodynamics of sea ice, and both here in the Arctic, that's on the right, and then also in the outer solar system, because these icy satellites are basically big chunks of sea ice. So those are the things that I'm working on. Oh, in advance.
I guess that's me. Thank you. Good morning, everyone. I'm Helen Cerisi. I'm an associate professor in the Thayer School of Engineering. And in my lab, we work on understanding and modeling the evolution of the Antarctic and Greenland ice sheet. And I presented already this morning what I doing in my lab, so I'm not going to repeat that. Instead, because this is a panel on modeling, I thought I put just like some cartoony slides. And the first one here is like,
a number of people say that we need to better model and represent ice sheets because it's one of the main contributors to sea level rise. And these, I hope I'm not done already. So here you have the number of people who complain about ice sheet models not being good enough and not having enough projections. And in white you have the number, and this is probably exaggerated, it's even smaller. The number of people who actually model ice sheets and try to improve these projections. Another interesting fact, or call that whatever you want, is that over the past decade, the number of observations of polar ice that we have been acquired has been increasing exponentially, and at the same time, the number of new physical processes that people are discovering on small scale, large scale, the surface, the base, in the interior, and the coast, has been increasing exponentially. And on the right, you see over the same time scale, the number of these physical processes that are actually included in the ISO models. And I can name, I have no idea who's on that left side. I can name every single process that we've been added on the models. Grounding line migration, ice front evolution, better thermal models. What's the last one? I don't know. But like very, very few processes actually make it in the model because it takes a lot of time to implement them, validate them, calibrate, and include that in large scale projections. So how do we do that? Which one do we choose? And what is important to add in these models as we have more observations and more things that people discover every day? One last slide about models. There is a variety of models. We have here 2 models of an airplane. The first one, if I ask my kids are too old now, but like you ask any 3-year-old kid to do that, they will do that in a second, just take the piece and that'll be done. On the right, we have a lot more pieces, a lot more sophisticated processes. Maybe you capture better how a plane will work, the shape of the wings and the engines and all of that. Obviously, that takes an awful lot of time to build something like that. That's probably a bit more realistic, but also takes a lot more time. So how do we decide what kind of models we need to use for what purpose? So I'm going to stop there. I'm happy to discuss any of these topics in the discussion.
Hey everyone, this is the perfect segue for me. So this shows actually, my slides are much less funny compared to what we're presenting. So I'm going to start with this slide. This is what I primarily This is what I studied for my PhD. I studied aviation and I did a lot of work on applied math and computing for as applied to aviation systems. And then I got interested in various other areas and I eventually wondered, what can I do that's particularly useful, right? And so that led me to some of these topic areas, some of these questions that I'm going to talk about in the next 2 slides here. So I don't have any grand vision for how we can use modeling to solve climate change. I'm too new to the field to have anything to say on that topic. But what I would like to give you is some examples of things we have been doing, very concrete things, and hopefully that generates some excitement and some new ideas. So one of the first things I started looking into along with Lily, who is here, and Professor Lawrence Debo from Tuck School of Business, is what can we do, if anything, about the problem of the large amount of food waste that happens, not just in the US, but many parts of the world. In particular, in the US, a lot of the food is wasted after it is sold at the household levels. And at the same time, we know that there's a lot of food insecurity. So we started looking at various ways we can more sustainably dispose of food waste. So that led to our problem statement of how to design food waste disposal systems by optimizing the cost emission convenience trade-off. And that's one of the projects that is ongoing right now in our group. And so what we try to do is estimate the overall impact of food waste on the climate and economy, and then talk about how we can use math optimization methods to optimize that. So that's something that I'm happy to talk about as the panel progresses. Much more recently, though, we've been working with a small grant from Irving and in collaboration with the Dickey Center for International Understanding and with PhD students Lily Yang and Sichi Kerr, looking at the question of energy transitions in fragile states, in particular in Africa. So the specific states we are talking about here include Central African Republic, Mali, Somalia, the Republic of South Sudan, and the Democratic Republic of Congo. You will see roughly where they are in the overall scheme of things in Africa. So As we know, a lot of discussion today and in many other venues that you've looked at has focused on how can we move the energy transition, or how can we move the energy systems toward more sustainable systems, especially in parts of the world that consume a lot of electricity. That is a really important question, obviously. But then there are a lot of parts of the world where there is almost no electricity. So then the question is, can we think of this as an opportunity to have a sort of different trajectory towards more sustainable energy and electricity in those areas? So like I said, 60% of the 20 most energy poor countries are in conflict regions, especially in Africa. So we have started this project last month looking into some models and methods that we can develop to try to help decision makers in terms of building and deploying a systematic multi-stakeholder decision-making framework. Multi-stakeholder is the big word here, really important because it's not clear who we need to cater to in these areas. So this is a fascinating topic, and hopefully in the coming few months we'll have something more interesting to say rather than showing a map of Africa. And then this is the topic that we talked about a few minutes ago, if you were still here at that time. This is a summary of what I said. I'm not going to go into it, but the point here is that we can actually use the power of deep learning and artificial intelligence to help us in the tactical level to try to fight wildfires that are already, but also at the more strategic level where we can try to understand how much resources are needed and how do we allocate budgets to do these firefighting operations. And finally, this is joint work with Klaus and looking at flood mitigation and beach nourishment versus managed retreat. So as we know, the sea levels are rising and storms are increasing in strength and intensity and frequency. So the question then is, can we keep protecting our communities against these storm surges, or would there be a time where we need to retreat and go backwards? So the idea of managed retreat is often overlooked, and there are a lot of complexities. There's some data here. I don't want to go into the details right now, but the point is that the cost benefit analysis are pretty complicated, and there is a deep uncertainty and a very long time period that you need to look at when you make these key decisions regarding retreat and regarding protection. There are many different decision makers involved, and so the methods and models we need to look at are complicated. They can involve optimization under uncertainty, but also game theory and mechanism design. So those are the things that we are looking at, and the key idea here is to acknowledge that there are many different objectives and we need to explicitly account for them. So these are some examples that I would love to talk more about. Thank you.
Thank you very much, everyone. So we can open now the floor to any questions to the panelists.
There's two questions, but I don't want to follow. But time permitting, I'll come to the second one later. The first question is for Erin. That map that you put up for 2050, what are the land use implications of that?
Yeah, so we do estimate the land use implications in terms of direct footprint in addition to visual impacts, because that's a large part of the impacts associated with transmission and wind. We look at kind of we create those algorithms looking at different land use patterns and different land use restrictions, and also different permissivity in terms of permitting regime. So that is an important aspect, the land use aspects. That being said, we can't just think about the land use impacts from renewables in isolation from the land use impacts associated with a bunch of other types of incumbent infrastructure like fossil fuels. So.
Right, but what is there a net effect that you're able to come to a conclusion on?
Yes, we have quantitative estimates of net effects. Off the top of my head, I don't know the numbers, but it's from a direct land use perspective, it's on the order of kind of the size of the state of Kansas, if you kind of look aggregate across kind of the US.
I'm curious for all the panelists' opinion on this. How useful do you think your models are for informing decisions? And how do you try to negotiate the conflict between all of the challenges in modeling and in climate context, the need to make decisions now? Part of thoughts.
Well, borrowing the picture from my esteemed colleague, the proof of pudding's in the eating. And if the kid picks up the easy airplane and plays with it, that's success. And so I think sometimes a faster, more user-friendly model that actually is being used, obviously is better for decision making, However, there's a tension between the simplicity and with what you can publish in high impact journals. And I think we need to navigate those trade-offs very carefully. Maybe more for junior people than for senior people, but we'll talk more about this later.
So most of my work in answering that question is adding the small little Lego pieces from the simple model onto the more complex model. And so sometimes I ask myself a similar question, sort of like what intrinsic value is improving this physical practice going to be? You know, as Helen said, it takes a long time for these things to be adopted into ice sheet models. Some of the things that I've worked on may not in my lifetime be implemented in ice sheet models or may never be implemented. And I think that that's okay because we're trying to build fidelity to, you know, to understanding this system much better. I think that, yeah, I think that's what I'll say on that.
I see it as the complexity of the model is dictated by the decision context and also the time horizon you have to actually make the decision. So this is a constant conflict in all kind of the modeling that we do. We want to inform decisions. If it's a high level just agenda setting decision, the broadest contours are fine. So reducing complexity is fine. But if we're trying to kind of implement or do something on the ground, we want more resolution in what we're trying to inform it.
I think all models are wrong and some are useful. So let's make sure that the models we do and the experiments we do are useful. I think also we need to. This was obviously very provocative thoughts, but I think we need to. Two things. We need to stay away from this dichotomy, or we use simple models or more complex models. We need to figure out ways to combine them, because in one case, you can do many experiments with lots of different forcing, carbon emission scenario, whatever you want, and have lots of results. And you're going to lose some accuracy. Yeah, I mean, obviously. On the other case, you're going to have models that are a lot more expensive to build and expensive to run as well. And so you can do a handful of simulations with that. So I think we need to move away from these trying to say, oh, simple models, complex models. We have to have a variety of models, different level of complexity, and be able to integrate them together if we want to move forward. Another thing is that Colin was talking about all these new processes and things that we might be able and want to add to models. I think a lot of my job is also like thinking about what's the number one thing that is the limit in my current model. There's no point in refining something for which we have no information, we have no data, and has going to have an impact of like 0.001%. You want to go after what's the number one order of magnitude limitation in your model, try to focus on these processes, implement them, validate them, and then go back to your simulation and figure out, okay, now that I've made some progress in that, what's the next big limitation in the model, and try to think about the key things and trying to put some priorities on all these processes.
All right, so I just want to kind of echo what Erin said a little bit, but differently. So a lot of my work is in decision making in many different areas, and many times one wonders, what does it mean by decision making? Are we trying to pitch this to, say, a C-suite executive saying, okay, please do this at the strategic level in a company or organization, or are we talking about working with the person who works in the trenches, trying to fight these fires or something like that? So depending on which audience we are catering to, I think the decision-making models will need to be tuned to that. For example, if you want to look at the big picture policy question of whether a certain type of demand profile means that you have a 60% solar, 30% wind, and 10% something else, or do you want 30, 60, 10 instead of 60, 30, 10? That's a higher level question. How do you go on and execute that? It's a low level detail, so we can try to disentangle these things and talk about models that are slightly simplified to incorporate the system-wide complexities in a slightly simpler way. On the other hand, if you want to help somebody who is trying to deploy resources and you say to them, yeah, generally have a bunch of trucks and maybe twice that of airplanes ready and do something good with it, that's not useful, right? So I think the question dictates the answer, and in a lot of cases, the question that it comes down to is who is the person or organization, or more specifically, the unit within the organization that you're trying to help out.
Great. Any other questions?
Just following on that, I guess I wondered how much each of you spends in time talking to, communicating to stakeholders that use your information.
Good reverse.
It's a big volunteer kind of time sink. I'm just wondering about that. Yeah.
Obviously not enough. And what I've been doing is mostly provide information that can be used in like reports like IPCC and things like that, that people summarize all the research and prepare things for policymakers and stakeholders. I haven't really interacted that much with stakeholders. I think I know I should do it a little more, just like time is limited. I'm not an expert in that, so I feel like it's maybe more valuable for me to be able to provide better projections and think about what's limiting. But when I talk to them, I realize like how much I should do it more. So not enough is the answer, I guess. You want to start that way? Okay, let's start like.
Well, let's look around in the room, and I think the person does this right now best is Erin, because he actually has this sustained and not extractive, and I think it's really helpful. The point here is that we need to be aware that this is difficult, and just because you're a PhD in something doesn't mean you're really good at stakeholder engagement. Just because you talk to someone doesn't mean that you actually talk with someone and you get something out. And we have to be really, there is real research to be done. And I think it's really important to also recognize what's the support structure. If someone would like to do that and is a student or postdoc and it takes 3 to 5 years to have trust, that's not a time scale for a single person to establish this. So we need longer time scales of memory, of institutional commitment to actually do so. And I think that's something which here in Dartmouth and in Irving potentially one could do, because this is, in my view, beyond the time scale of a single lab group or a single PhD or postdoc, but just my opinion.
One thing I'll add, taking this in a slightly different direction, is thinking about NSF broader impacts. And one of the things that when I talk to program managers, they really value being at a university because, I'm not directly talking to the stakeholders in Miami about sea level rise and that sort of thing, but I am talking to next generation students, right? If I go do outreach at an elementary school, I'm talking about the future. And so that's a place that we almost don't have to change anything about our jobs. We as educators we're interacting with future stakeholders. And so bringing in the things that we are learning into our classroom has that value, and we're in a really good position to do that.
So the nature of stakeholder engagement differs across the different decision contexts. So it can range from just informing to actually co-developing solutions. So for example, the past 5 years, I've been working on kind of federal policy and net zero futures. Most of that has been in terms of informing, where stakeholders reach out to me and I provide information. So over the past few years, I've provided like 50 presentations to niche audiences related to these net zero futures. On the other end of the spectrum is kind of work, for example, related to steel decarbonization in the US, where we spent a few years just fostering relationships in these steel communities and had co-partners within communities to actually kind of develop these projects. And now we're only starting to actually do the research itself. And so that is kind of truly on the other side of the spectrum where we're doing the co-development.
Yeah, I think I don't have much else to add, but I think I would say that again, how much and what kind of stakeholder engagement you want to do, which by the way is very important in general, but how much and what kind do you do sort of depends on what you're trying to achieve. For example, on the one end, you might argue that one of the ultimate goals should be to develop methods, ideas, technology, and then deploy it in specific contexts. That's amazing. In that case, you want to have specific stakeholders and you want to know exactly about their specific questions and how we can deal with them. There is a risk there. It's a slightly slippery slope, even though it feels amazing to have done this, and I've done that a few times in different contexts. And it feels amazing, but then the question is how generalizable something is. So that then means that you want to develop these relationships with the stakeholders, but then you don't want to overcommit to a particular way of thinking about the problem, because that may or may not apply to other contexts, other users, other stakeholders. So that then takes its own life. It can then become an entire project by itself, trying to figure out at what level you want to, how specific you want to be with your way of defining the problem statement, and And at the one end, you can be very specific and satisfy one individual, their needs, that community's needs, etc. But then it might be fairly non-usable for anybody else. On the other hand, you can try to be generic, but then there is a risk that you may not have even a single use case to show for it. So it's challenging. I think stakeholder engagement, like some of my colleagues have said, and you have said, it takes up a lot of time, but it's nevertheless extremely important. So this is one of the places where all academics can use very smart and efficient help from on-campus resources, just to pitch in for that again.
Thank you.
We'll end up with the mic. So
there's one more question.
Thank you so much for your presentation. And I work with local production and I'm on the side of indigenous communities. And what I see now is that we have a lot of conversations related to risk management, green transition, and all of that based on that data-driven approach. So indigenous knowledge is not included in the data sets, and often when I go to conferences, even the companies, I see, like, for example, as a key project that they put like all this, let's develop plans, I don't know, like all these pipelines and stuff like that, right? They say like they have that data set, and then I ask like, you use indigenous lands, for example, for indigenous knowledge, and they say we don't have that data set to put in that to sell to companies who make decisions about projects. My question is how we can implement indigenous knowledge and make it like this data set equitable and full of knowledge to you, because I don't know how to make those models. So maybe you have thoughts about it? Thank you.
Take this.
So I think it's first acknowledging that the forms of information and knowledge aren't just data. A lot of what we do in my lab are data driven, but that is contextualized with other types of knowledge, or other types of knowledge often is more important in the decision-making processes. I can even say kind of the way a lot of the information that is consumed that comes out of our lab, it's the broadest contours of what we're actually doing that people care about. It's not the actual kind of data itself. And so I don't know specifically with respect to indigenous knowledge, but I see kind of there's the point at which it's providing kind of context and actually often probably more salient for a decision-making process than kind of the data itself.
I'm happy to give it a try. So there's a big push for that, and if you were here this morning when Margaret was talking, was co-production of knowledge, including indigenous knowledge and defining research questions and topics with that in mind. For what I do, there are lots of challenges. We want to work with communities in Greenland that speak a different language. These are hard places to access, and so there are additional challenges, and it takes a lot of time to build trust. Which unfortunately we don't make enough time for that. So these are additional barriers, and I know that many people want to do this more, and it seems like on both sides, people want to work together, but it's really still hard to make connections and have people connect and work together. So I think we should continue to talk to each other and learn from each other so that we want to make this happen. And it won't happen overnight, but like as was said already, by building these trust and these relationships over a longer time scale, we can start connecting and really learn from each other and work together because we have the same objective in the end.
I think we're running out of time, and actually I think it was a great question to end the panel, and hopefully this type of events and the Irving Institute can be provide an environment where people can bridge some of these gaps. So please join me in thanking our panelists for
Start our second panel of the day today. Thank you so much, everyone, for being here. My name is Amanda Graham. I am the academic director at the Irving Institute for Energy and Society. And I'm very pleased to welcome you to this panel on carbon sequestration. We have a very interesting lineup of folks who are going to give you multiple perspectives on this very important and emerging area of engagement in energy and climate solutions. And so without further ado, I'm going to go ahead and give the very quick introduction of our panelists in the order in which we're going to go. And then they will give their 3-minute talks, and then we'll follow that up with a discussion and questions and answers. So we're going to start our conversation with Professor Anant Sundaram, who is Clinical Professor of Business Administration at Tuck. Our second panelist will be Chris Snyder, who is the Joel Z. and Susan Hyatt Professor of Economics. Chris is followed up by Mukul Sharma, who is Professor of Earth Sciences. And then batting fourth is Caitlin Hicks-Priest, Associate Professor of Biological Sciences. So with that, let me hand the mic over to Anant, and you don't have to sit, you can sit.
Oh,
it's okay.
Great, yeah. A couple of notes in case I want to look at them. My 3 minutes are on CDR and MRV. CDR, carbon dioxide removal. Without that, no reasonable solution to net zero within a reasonable time frame, within a reasonable temperature range is possible. 2, however, CDR is basically pointless without MRV or monitoring, reporting, and verification. And 3, it's a wicked problem when it comes to the current methods that are out there that are being explored for CDR. So I'll just go through a few of those and happy to expand later in the Q&A. I'm basically under most reasonable scenarios of where end of century temperatures will be and what our carbon budget is, etc. Problem is there are residual emissions, aviation, shipping, structural materials, baseload electricity. There are a bunch of things that it's impossible to get on, realistically speaking. And so we will need to balance the emissions with carbon sinks. And according to a range, depending on the scenario that you assume, you need something over the next 65 years or so, to the end of the century, of something between 300 to 750 gigatons of greenhouse gases that need to be put away for good, and we capture it and find alternative uses for it. And of course, the more stringent the temperature target, closer to 1.5 degrees, the more the CDR we're going to need. The worse the emission scenario, the more the CDR that we're going to need. So when we say CDR, what do we mean? They're basically both nature and technology-based removals of CO2 from the Earth's atmosphere. And this is critical to durably and with minimizing the likelihood of leakages and so on, store it on land or sea or in terrestrial aquifers. There are about 6 to 7 at this point, broadly that people agree on as methods of CDR. One is the obvious one you all know, which is afforestation and deforestation. The second potentially big one is biochar, soil carbon restoration technologies. And there's something called BECCS, BECCS, bioenergy, carbon capture and storage. Then there's something that's huge potentially called DACS, direct air carbon capture and storage. And there's something called enhanced rock weathering. And then finally, the ocean as a sink in terms of ocean fertilization or alkalinization of the ocean. So what's MRV then? Without MRV, first of all, if you're going to measure something, we can't manage. If you're going to measure the quantity of something credibly, we can't put a price on it. So you're going to have a carbon price that's incentiveless investments in this area. So the question is, how do we, and by the way, no one will believe our numbers and should believe our numbers because people lie. So how do we assess the veracity of claims that are being made? 2, how do we get assurance on durability and leakages associated with what we put away? 3, and this is extremely difficult, the science gets very hard here in many of these areas, how do we ensure tests of additionality? In other words, there has to be a baseline over which we are removing stuff. So how do we define and measure that baseline? And 4, how do you make sure there's no double counting? Again, people will still sell the same stuff twice and, double dip. And so we need carbon registries, in other words. And perhaps equally, if not more, and most importantly, how do we make sure that this is not harmful to communities and environments? And in closing, so the process finally of getting to MRV will ultimately involve, coming up with science-based baselines, collecting data on the actual CO2 put away. How do you get it audited by third party, who we have to skill them to do that? How do we then get it verified by people who set the standards? And finally, we need to set carbon registries and exchanges in which things like double counting and additionality problems are at rest. So let me stop there and pass it on.
And thank you so much for setting the stage for us in terms of the urgency as well as some of those critical challenges. Chris, what's the economic perspective?
Yeah, I think I have some slides here.
You do. I think you have a pointer.
The big button.
Yeah, no, that's fine. You can go next. We'll just go ahead to yours. No. Oh, wait. Not doing well. Is that yours?
Nope.
That's
Is
that yours?
So hi, I'm Chris Snyder from the economics department. So I teach micro theory and the economics of firms. So what would I have to say about CDR? Mainly I'm interested in, I have a policy interface here. And so I've been working on policy in this area in two dimensions. One, I'm working on this, essentially this policy startup with some colleagues at the University of Chicago. We call ourselves the Market Shaping Accelerator. And so basically our shtick is that we're trying to advise and advocate for so-called pull funding for innovations to meet global challenges. By pull funding, I mean, instead of say grant funding for attempts, we're thinking about paying for outcomes. So actual production, in this case, actual removal of carbon. And so we think that in some cases, push funding for sure is very useful for many innovations, maybe most, but in some cases, maybe there's a role for this pull funding. So we're looking at cases where there's a wedge between the social value in a market and the commercial incentives for firms to provide the products that we need. And so two cases would be, climate is certainly a big one there because of the environmental externality. So what do we mean by market shaping? We're looking at various funding mechanisms that pay for results. So a prize for an innovation, for the coming up of an idea that solves a problem. It might be advanced purchase commitments that you might put together for CDR, or they're more esoteric contracts like advanced market commitments, which are actually firm agnostic contracts. We're looking at two areas, and that's just what our funder who provided us with the funding is interested in initially, and those are pandemic preparedness and, more relevant for today, climate mitigation. So we provide advice to various stakeholders that come to us, but in a sense, to get ourselves off the ground, we actually, in a sense, launched a payment for results, in this case, payment for ideas in this innovation challenge in these two spaces. So some of our grant funding went towards basically $2 million of prize money to provide ideas. And we got 190 submissions from agencies ranging from the Department of Energy to private individuals and people all over the world in those two spaces. So we're going through and kind of selecting winners. We got it winnowed down to 7 different projects, which we can talk about. Another policy role I've had is an advisor on an advanced market commitment put together by Frontier, which was funded by some big tech firms, including Stripe, that basically socially concerned firms that said, we're interested in honoring our net zero commitment with high quality offsets, not just, paying $1 not to cut down this tree, but then you cut down this tree, but, high quality offsets. So carbon removal would be one of those that has the properties that are not talked about, additionality and durability. So let me just go to this. So these are basically the Frontier. They raised $1.2 billion, and these are the projects that they've put their funding towards. So what they're doing is they're basically signing purchase commitments for actual carbon removal by firms working in these different industries. We have, and then I talked about each one of these, ocean alkalinity enhancement, biomass, carbon removal, enhanced rock weathering, direct air captures, and
in the black there and direct ocean removal. You can see that these purchases are, this is purchase price per ton of carbon removed. And they're extremely high prices paid, right? Much higher than what we'd consider the government, US government considers the social cost of carbon. Erin, what's today's social cost of carbon?
Officially $50.
$50.
Changing soon, right?
I told her, I promised Erin Mansur that I'd bring him in. So you can see these prices are much higher than that. They're 10 times that. So the thought is that you can maybe march firms down their cost curve. They're not necessarily going after the lowest cost technologies now, but maybe the ones with the most promise. So here you have in a sense, a well-intentioned czar that's kind of meeting firms at their price point and hopefully marching down. You can see that these are pretty high prices. The largest procurements have been for lower prices. That's, I guess, reassuring. But the question is what to do next. What's going to be, this is $1.2 billion. That's a tiny fraction, a minuscule fraction of the CDR we're going to need. We're going to need, $1 trillion market eventually. So, what should that market look like? I mentioned this innovation challenge. Here are some of the climate projects that we're going to push forward, and you can see that one of them is one of the chief ones is carbon removal. So we're talking to the Bezos Earth Fund about maybe organizing kind of what the big picture for the world is going to look like for carbon removal. Is there enough scope to remove the carbon that we need by some whatever temperature target we have? And then how best to affect that, and what kind of an international agreements we're going to need to do that. But I've gone over time. Let me kick it over to
Okay, so thank you, Chris, for some of the economic tools and innovations that are on the table here, and looking for Moonkle to share with us some perspectives on technology. However, speaking of technology. Thank you, Angie.
Yeah. Well, in the meantime, good afternoon, everyone. And I'm absolutely blown away by the talent we have at Dartmouth in terms of what people are doing in terms energy impacts us all, and climate is a big part of that energy. And what I see is that that we as a community can make a serious impact from health to biofuels to financing to businesses in climate and in understanding fixing the climate. So
they're not there yet. I'm trying to get
all right.
Yeah.
So what I'm doing is my field area, just like many other people, I'm working in an area now which I never thought of working in. My field is isotope geochemistry, which means that I get to work on everything under the sun, and including the sun. So I've studied solar physics, and I've studied fracking and ocean chemistry, deep time climate changes that are taking place, changes in the sun's magnetic activity and how it may have impacted the Earth's climate, etc., etc. Lots of different things. But being at Dartmouth, you get to teach courses to such very fantastic undergraduate students, and one of them is about Earth resources. And I realized at that time that in fact that I could contribute something to it, to learning about Earth resources and climate change associated with it, and realized one thing was that I was, and just like every one of us, we are witnessing a slow train wreck. Okay, that's climate change. And so the question to me is not how to document it. The question to me is how to fix it. Okay, and so I have come up with two different strategies to fix this problem, and I'll try to get some money out of him. Shove it, yeah. The first strategy it has to do with removing carbon in the ocean. Okay, so the procedures, the strategies that Anant has talked about, most of these strategies, in fact, are highly industrial, and they will require a huge amount of effort, money, and of course, energy to bury CO2. For example, that's serious problem. Okay, there are the two ideas. All right. So the big idea is to sequester atmospheric CO2 by utilizing clay minerals. I'm a geochemist. So I understand something about clay minerals. And okay, I will try not to mess it up. Okay. So the gray one, how about the pointer?
Pointer
right there, yeah.
The top one, the one with the dot.
The one in the top.
Yes.
Oh,
Yeah,
man.
yeah, it's tricky holding it.
That's pretty cool. So I just stand up. But I was going to point it there, but I don't think it worked. So, oh man.
I've never seen.
There you go.
It disappears.
No, keep holding it. There you go.
Holy cow. It doesn't seem to be working as I intended to work, because as I press it, it disappears. After a while it stops. Anyway, so you see, the problem is there is 5 billion tons of carbon. Now, carbon is not CO2, that will be much higher. Yeah, that is how much there is you have in the atmosphere. That's growing every year. Okay, and our strategies are to remove them in the ocean and remove it in the land. Not all of it, but substantial amount of it, which is because using nature-based solutions, things that can be accelerated. So the idea number one is to recruit the marine biological pump with clay minerals. Now, the ocean every year, they take out about 50 billion tons of carbon, 50 billion tons of carbon, and they release it right back. The carbon that they're taking it out is using the biological pump. That is, little phytoplanktons that do photosynthesis, they take carbon out. And then what happens next is that they get grazed upon as they die, and then bacteria take over and convert all that carbon that they have fixed right back into CO2. And that gets out. Okay, so that's about 50 billion tons of CO2, carbon, sorry. So about 200 billion tons of CO2 is exchanging hands between atmosphere and the ocean every year. Okay, so if one can remove even a small fraction of it by recruiting this pump and bury it deeper, one comes out as a winner, even if small fraction of that 200 billion tons of CO2, all right? So that's the idea number one. And how that clay minerals come to play is that clay minerals can in fact increase the burial rate of carbon that is being produced in the surface. That's the experiments that we have done in the laboratory and also in the Gulf of Maine to understand what is going on there in terms of removing that carbon from the surface of the ocean to some great depth. That's all that you need to take out that carbon. Okay, we don't know the efficiency yet. So the MRV problem that Anand talked about is a serious, important problem, but we are not there yet. We need to get there. The other one is a simpler problem that can be actually, a strategy is a simpler strategy that can be actually used by Mama Papa operations. Okay, and that is fortified biochar, where we can bury carbon in the soil and at the same time change the alkalinity of the ocean that Anand was talking about. And in doing so, remove carbon from the atmosphere. Bulk of that carbon, lab experiments show that will be sitting in the soil, not because the alkalinity changes are long-term, smaller changes that take place from our concoction. So these are the two strategies. I see that that there were other slides. That's one, and the other one is this. So I'm just super excited that we have a reactor from MIT that we are now creating. This that will be used to create something what I call fortified biochar, and you can see that a plant grows better with a fortified biochar than with a basalt, with the biochar itself, etc. So this is a procedure that would allow us to remove CO2 on land. Thanks.
Great, thank you so much. I'm going to pass you this. Okay, Caitlin, tell us about soils.
Yeah, so I'm a terrestrial biogeochemist, so that means I work on land, and my focus has been on soils. And I look at soils as both a potential to be our friend when it comes to climate change or our foe. Currently, soils store about 3,000 petagrams of carbon, so that's more than three times as much as our atmosphere. Our atmosphere has about 800 petagrams of carbon. And one of the big questions is, with climate change, how much of this carbon that's currently stored in soils could be released to the atmosphere? So that's the faux part, where soil carbon might be working against us in the future. But then there's also this potential for them to be our friend, where we can change our management practices and put carbon from the atmosphere into the soils via better farm management, increasing plant growth, biochar, like Nicole was talking about. There's a lot of different options that we're looking into to see how we can enhance carbon storage in soils. But all of these are going to be kind of engaged in an uphill battle, because the fact is, as it gets warmer, microbial activity in the soil increases. And as that increases, that means decomposition increases. So more carbon stored in soils, stored as organic carbon, is being decomposed by microbes and then respired out as CO2. So that is a positive feedback to climate change. So all of our management and natural climate solution efforts when it comes to soils are going to have to be working against the fact that some soils, especially those in permafrost region in the Arctic, are going to be losing more carbon as a result of climate change. However, we've already abused our soils a bunch. So one estimate is that since the dawn of agriculture, we have lost 120 petagrams of soil carbon as a result of intensive farm management. And that 120 petagrams does represent an opportunity where better management, we can put that carbon back into the soils. There are some people who are really optimistic about this. There's one group called the 4 per mil group that came out of the Paris COP agreement, sometime in the teens, I can't remember when. And their estimate is that if we could increase soil carbon by 4 per mil, so by 4,000 every year across all of our sort of arable land, agricultural land, that we could that would make up for our emissions on an annual basis. So that is very pie in the sky, but they did that calculation just to show what the potential is for better management. A lot of what my lab does is looking at both sides of the equation. So we're looking at climate change experiments, seeing how warming is affecting the existing soil carbon that's there, but also working with farmers around Vermont and northern New England and measuring how much carbon they have in their pastures and how their management practices are affecting the amount of carbon and how that carbon is stored and how vulnerable it is to being lost with climate change. So we've been one farm we're working with is Wolf's Neck, which is an educational farm dairy operation up on the coast of Maine that's very much engaged in education around climate and regenerative agriculture. So we have an eddy covariance tower there, and we're measuring what the carbon balance of their pastures are. We've also been working with farmers, dairy farmers and cattle farmers throughout Vermont as they try to better manage their lands. Yeah.
Thank you so much for a diverse set of perspectives, right, on this, emerging and a huge potential area, also huge controversy, right, as folks are trying to figure out where do we fall down in terms of the environmental benefits and challenges, the social benefits and challenges, the economic benefits and challenges. So thank you, panel, for presenting these diverse perspectives. This is your opportunity to ask questions, to share your provocations, your concerns, your ideas. Questions from the audience on carbon sequestration for our panelists.
Yes, I have a question. I'm Donna Consolini. I'm a fundraiser at Dartmouth. Very impressed with all these practical ideas that I've been hearing about. How have you presented these ideas to funders, whether it's government funding or companies, foundations, individuals? These are great, so I'm just curious to know about the funding sources for this work.
You're directing this question.
And any of you, yeah.
Well, he's the funder. I received funding first from Guggenheim Foundation as an award, and then through Schmidt Futures, through Grantham Foundation, through Esther Institute. So, and the way I presented it is more extensive than this, but certainly this is a the motivation is there. They were able to believe in me, a present in this area, so to speak, who had only come up with some new interesting ideas, thinking in a very different way, out of box type of situation. So they believe in me, and therefore they funded me.
That's great. And are they funding you to actually do more of this, to see how it's working on a larger scale and openings and?
Yes, so I warned them that they gave me equivalent of about $2.5 million, and I warned them that was phase one. And the next one was going to be 10 times more for ocean, especially.
Any other responses to the funding?
So this market shaping accelerator, we got a grant from Schmidt Futures. So they gave, I think it was all total $5 million to basically put together. It's not all to pay our salaries. In fact, none of it's to pay our salaries, but some of it's for the prize money that I was mentioning, for payments for these, basically these, as we funnel the ideas to completion. Oh, by the way, that's, $2 million is not what we're talking about for the market shaping, the funding project. It's, something in CDR might be a $10 billion program. But this is just for maybe in a sense, the pro bono consulting we're providing on these things. It's not a very lucrative profession, pro bono consulting. That's so that helps defray some of the expenses. But then we've been in a sense trying to franchise ourselves out. So Schmidt Futures, we just launched in May, and Schmidt Futures were like, why aren't you doing 10 times more than you're doing? So they're excited about, we just are limited in terms of time. So we're trying to franchise ourselves out. I'm for example, trying to get my colleague Erin Mansur on board and things. And so take some of these projects, you saw that list of ideas, and sort of farm those out to different people. But anyway, that's the reason that we're able to raise as much money is not on my strength as a fundraiser. We're actually, one of my partners, his name is Michael Kramer, won the Nobel Prize in Economics. So people know to go find a Nobel Prize winner and provide him money. And so some of it filters down to the peasants.
Other questions from the audience? So Erin and then Bob.
So Chris, I was wondering if you could talk a little bit about timing. Like for some of these types of things, it might be a 10, 20-year kind of investment. Is that something that is a credible commitment for an organization such as this one? Like, if I think I have to put up that much money to take this risk, will the organization be there in 20 years when I go to claim my prize?
So whether our organization is there, we're hoping to design mechanisms and contracts that are durable. So one of the areas we said we're working on kind of pandemic preparedness and climate. Actually, we came to this more from the vaccine or pandemic preparedness space, and some of the ideas we proposed. One of them was a pilot program for vaccines for poor countries, and they piloted it for a second generation pneumococcal vaccine. So that they raised something like $1.6 billion from the Gates Foundation and other finance ministries. And we're talking about like 10-year contracts there, and or 15-year contracts. And so they actually piloted it and they ran it, and it's the program that was piloted early in this century. And so it's actually run its course and credited for saving something like, or at least the vaccine, not the program necessarily, 700,000 lives of children under 5. So these programs can be durable. So for carbon removal, the frontier commitment, it's a good question, but I think the money's there in a fund and it's committed. They're having trouble spending the money right now, so that's the problem. So it's not running out of money, but it's actually spending the money. So please bring your ideas, and they'll fund those. But I think we're looking for a much more, much bolder program that's going to be a much larger commitment that actually will spur the investments that might get us to scale. So I think we have to be looking at a 10-year horizon and a lot more money. We can't be looking at a 50-year horizon because, then we're sunk. So I think a 10-year horizon is probably the sweet spot.
So, CDR is an approach to repair things or not heal with them. As a physician, I'm used to most of the things that I do come along with side effects. Most of our interventions include health. I'm just curious about the potential for side effects that we think would help me that we're trying to reverse, if you will, some of the damage that it caused. But we try to reverse damage in individuals, cause problems. So has any work been done to have kind of ecosystem damage that could potentially occur? The short answer is absolutely none. I mean, it's wide open. I mean, the externalities associated with this, both positive and negative, are just so poorly understood at this stage. And then we could even get to bigger ones. But some of these sort of get into, geoengineering kind of solutions, and going to be super careful about. And there's an issue also of, one country can't just start fertilizing the ocean without, say, the US can't just start doing it without bringing in Canada and Mexico. And then soon before you know it, if China starts doing its own thing, India. So there are a lot of international agreements are needed, or none of that is anywhere near in place. We're barely getting started on it. On what is a 300 to 750 gigaton cumulative amount that has to be removed. You probably remember the number better than I do, Mukul. We're probably removing what about 50 million tons, 20 or something annually in that.
Total 2 million tons.
2 million, sorry. Yeah, so bottom line.
But there have been studies that have looked at what some of the negatives are, especially, but not on the same scale, right? But the people are thinking of like, okay, if you fertilize the oceans, what does that mean for the ocean ecosystem? Like that has been looked at. I think, from an terrestrial ecosystem perspective, there's a lot of co-benefits actually, like soil carbon. There's this idea of soil health, and like healthy soils have more nutrients, they're better at growing plants, they're better for growing crops. And generally, like one of the number one predictors of soil health is the amount of soil carbon. So there are potential for a lot of co-benefits there. The risks that I've seen in terrestrial ecosystems oftentimes have to do with afforestation projects, where they're trying to forest an area that shouldn't have been forest to begin with. And they'll say, oh, we planted this many trees, but you go back 3 years later and all the trees are dead. Or by planting the trees, you've diverted water from communities that need it. And so I think in terms of terrestrial ecosystems, it really behooves us to look at what the history of what's there and what can grow in that climate or in the future climate, and pay attention to that, and not just try to like make everything very cookie cutter. But we definitely consider it.
Yeah, just to add that, CDR is like going to the moon. Okay, and that's how we consider, as scientists, we consider that. That is, you want to have, each baby step taken and make sure that in fact there is no problem associated with it. So the ocean strategy that I talked about, we are doing microcosms, mesocosms, followed by the mesoscale experiments. And every time you want to look at what are the collateral damages that might be taking place. And then you say, oh, this is really bad, let's just stop it there. You see that, so it's not that we are simply going to go sort of full throttle and say, what with some idea that this is what we're going to do. Absolutely right. For land, it is far superior. It is as complex as the ocean, but it is easier to handle because we have been farming, for example, for a long time. So we understand somewhat better what can happen, and we can do that in a limited fashion. All this testing needs to be done first for experiments like the one that I planned. We're going to do it in Dartmouth organic farm, for example.
So I want to thank everybody on the panel. I want to thank everybody for being here. We're over time at time for our next event, which is lunch. And that gives you great opportunity to follow up if you had a question that you didn't get to ask. But please join me in thanking our panel for introducing us to some of the challenges of
You talked about like the quantities. You talked about the externalities, you talked about different technologies. Yeah, you talked about the unification, additionality,
No, it's a.
I mean, that's cool.
Thank you. You did a great job.
You guys made it easy. And having multiple places, I think was radical. Thank you.
My day job.
Field scale.
Right. I guess that's a day job.
Yeah, to make it feel. I was working on taking basically it's biochemical process. Highly advanced.
It's not in.
So one of patient.
I've seen stuff.
With it, and then so we have like
Since he had worked on money work.
Yeah. Yeah. So it's like
vaccines.
Yeah, there's some evidence that
But then during the games, people actually on frontier.
Get to answer my question.
This idea is that you go.
That's 10 to 20 years.
Yeah.
Global multinationals,
And,
local companies.
Said, you know,
That was my question.
usually the use cases,
What
in this case, you see the use case here. So I wrote this out back and talked to her about the design of it. And then she went ahead and did things how she would. I mean, it sounds crazy, but $1.2 billion.
You know, I know.
The question is like,
Right.
once we realize.
I know, right. So it could be global multinational, but then the regulations might be local or national, right? So then I was like, what is that study industry growth?
We completed a
I just
campaign.
think of like
We are not in a campaign.
failure of solar panels.
So.
Yeah.
Like, with like a bunch of startups.
Yeah. It had all this.
This is tricky.
They were gonna be.
Makes sense. This is on here. It's on our side.
Got brought into the review committee, but it's.
I was thinking.
No, yeah, I don't think the age is going in.
So if we want to have that, we'll receive.
Oh, yeah, but now, the first part of the, try to get the point up. You don't have a skeleton.
And this, the
kind of the conveyor belt of you stop that. I'm not sure that the issue is there.
So now we get all this, the point I was, yeah, but it doesn't forward, that keeps things talking.
You gotta click it.
But that I am looking.
Not you, that.
Okay.
You gotta click, so bring the cursor up on the big screen, just go straight up and just click. You can see the little icon to the bottom left. Now you can advance it.
Okay.
So it's like, it's just making it the active screen. So anytime you come off and click anything, whether it's zoom controls, any of that type of stuff, it makes the zoom active window, so then the clicker doesn't really know. So it's gotta be up.
Got it, okay.
Like if you're used to running on one screen, you're right there, so it doesn't ever do it. The break is what's.
All right, thank you.
Is the lighting on purpose?
Yeah, because you know what, this is so nice.
Okay.
But I don't know, I did. Right, in front. I did. And then I brought it back again. And I really don't like it, back at the left, not in front, but it doesn't seem to be.
And you don't have access to programming.
Yes, yes, exactly, really, you have, really have extra. I think the read were.
Yeah.
That part,
That's everything, you just did it all of it. But yeah, so like the lighting. Go down to the program.
I did it, okay.
And then you can take and bring, okay, so it goes away.
Yeah.
But so this one, three, we need to.
Round three lighting.
I see.
Yeah, so now, yeah, my brain's always been great.
That's
So-
not bad, having a-
Thank you.
You're welcome.
No, it could be, yeah, they will, one.
Very good, very good.
How are you?
So is it weird not to have a kid and play this work?
Oh, I never have a kid to play.
I guess really sort of just get it out of private.
Really could hide behind the curtain. It's a little weird to be an empty nester, I would say that.
Yeah, we have one gone that's still on, so.
It's frolicking in Ireland. Or
Yeah.
Yeah. Some frolicking in South America.
Nice.
She will hang out with my wife's sister in Mexico for a while.
Awesome.
Because after 5 years of learning Spanish, she needs to learn Spanish. She's not to college.
Where will she go next year?
I'm still in Kenya.
Have you connected with New Peaks at all as we're starting to keep that?
Oh, no kidding. That's where Terry went. We're very plugged. But yeah, Sarah would have been.
Yeah, Sarah's one of the PhD students now, so she's been out for a while this year.
Well, it is one of those.
It was a good thing for her.
Yeah, it'll be great for Philip too. Just such a very big place.
Yeah. Yeah, I imagine Martin would be someplace like that.
Well, I like where all the resources go to the students. And I like where they're gonna light up both sides of their brains.
Yep. Hello. I'm like trying to reconcile this footprint with what we taught in here, what, 25 years ago? 4 years ago, whatever it was. I taught my first ever undergrad class in the old cook with that.
Well, the old cook and the new cook are basically the same cook. I'm surprised they didn't trash it when they redid the place.
Yeah, so it's sort of interesting coming down. I couldn't figure out how to get down here, but once I got down here, it was like, okay.
Yeah, and they made it seem familiar.
Maybe it's not a good-
It's actually one of the nicer airplane hangars you could lecture in, so I never minded this space. It was like says B-28, but if you cared,
Still 28 the one in the basement.
yeah, it's been redone. So there's 2 small classrooms on the basement floor, and then a real white elephant, techno charged big classroom on the first floor. Like we needed this.
It's good that it takes that out. Like, I remember coming to see Amory slaughter in here. And you'd like to have one place that's not, especially right now with the strap. What I remember is laying on the floor while you were lecturing because my back was spasming so bad. I was like out there alone.
Oh, I must have been focused on the car.
You were
I don't-
talking, we started walking back and Matt was like.
Man,
"I saw you."
your lecturing technique differs from mine. I've never made anybody spasm.
No.
Well, I try to have enough empathy so that if someone's in physical distress in the room, I notice.
It was, yeah. Those first 2 years till we figured out what was wrong with
And they're pretty much one of that.
So I have one leg that's shorter than the other. So as long as I have like basically an extra doctor shoes and so in the shoe.
No kidding.
But if I walk around, or I walk around in anything resembling a heel that feels me forward, I go back.
Well, getting the immediate negative feedback is probably good.
It is a really good example of why I didn't need a teaching hospital because we literally had a physical therapy student. I was treating my type of flex mind. I thought a lot of unexplained back pain is due to leg length. Just got that.
Okay, you had me until you told me that a student did the reading.
A student actually did their reading. It was amazing.
That's hot.
She was taking classes at Holy Spanish. It wasn't dark.
That explains.
But have that student off, they know that, right? They have been 5 years old.
And didn't answer.
No, no one had ever brought it up.
And it should be, seems like when you think of it, it's like, well, first thing to check.
No, no, wasted it. We really thought.
Well, we all have some.
Right. Our bodies can't. Speak word. So you're talking about something?
Yes.
Former neighbor.
Did you move?
You moved.
Just to North Deptford Road. I'm not far.
How are you?
Great, how are you?
Good.
So can you just give them a presentation?
Oh, I did see her name.
Yeah,
Yeah,
yeah.
awesome.
But she has a broken foot, so she's ankle, so she's.
Oh, no.
But I think she can get into the store without going downstairs.
Hi, Angie, how are you?
I like to go back to back with you. It's like we're.
Are you, yeah, I'm not sure what I got myself into here, but.
You only have
3 minutes. Let me just start throwing it something.
Something's like refreshment.
Good, she just came home for 2 days and then I felt right. She's super happy.
Cool.
Happier than, what?
Thoughts I lost in that.
Oh, no, good adventure. Oh, no. Okay. Good.
That's what I want.
Yeah. It was a little bit, I mean, she's super happy there, she's got lots of friends and we're boring, you know, and you come home and there's nobody else home. We both have friends in college, but my baby.
We were in preschool together.
Yeah. But she likes to shower. The showers in the dorm don't have much space. She has to go quickly. She likes to do. Actually, she gets leaving her own room, nobody's turning lights on.
As late as she wants.
Yeah.
Well, Thomas showed us, I guess.
Spencer got a dingle, as you call it. So he had made it a double, but his roommate never showed. So he on his own.
That's what we call it. Hey, the double red, because he kind of.
Yeah.
Cool.
That's mother's.
Where are they at? I don't even know.
Also Virginia Tech.
Virginia Tech. Yeah, hey, we have lots of friends there. And you?
My son is at the University of Chicago. Daughter is at. I've been in the road here.
Surprise me.
Because of COVID came, right? No, I think they're sports or. That's what.
I like about half.
What's easier for you, sitting or still
Sitting,
Yeah.
but I just, you know, it's kind of have to get up and speak.
Yeah.
At a certain point. I just want to make sure it's not like.
Maybe the unobstructed view and the extra leg room.
Those things, must be generally. I was trying to figure out a way. Oh, my God.
I used to be a professor for you. Fun things. Don't want that.
So when, that's like, real, you know.
Oh, I just, yeah, because I was, going to be doing it, so I cleared out. I think,
Maybe I should stop here.
yeah.
I didn't realize that.
Usually the cockpit is.
And I think it's sort of there.
Oh, I'm not in charge. I just. I start telling them. It's an egomaniac.
You know, you might want to just.
Yeah.
What?
Have somebody.
Someone will come at some point. Yep, so I'm Jackie. I'm also.
Yeah,
I have no idea. It's
nice to meet you.
Are you? I am. You can believe it.
And I like, I just feel like. And that's okay. And sometimes- And maybe therefore we take.
So this is one private. Yeah.
We'll see.
Thank you.
Yeah, we should have conversation.
Yeah. Yeah.
It's people that work.
All the upholstery.
Native people. So it's not, you know, in the summer, customs, media, that you go to.
Yeah, I'm actually gonna check that.
Yeah.
Sure, it's hard. Oh, yeah.
Right.
No, it's I remember these other things.
Oh,
good. No. Yeah, you gotta. Okay. You put a travel. Or maybe turn boring. Oh, really? Well, also.
Yeah, last year.
Before that, so I don't know if I can promise.
Yeah, great doing.
See that thing on radio?
It wasn't mine.
I'm
interested better. Well, practice.
I go over to 2:45.
I'm gonna go check it. I came in back.
This is quite a setup.
How is everyone? Visitor still here?
Yeah. Sorry?
Visitor still here?
Let's do it, yeah.
I sent an email when I sent.
Yeah, it's great.
Yeah,
and let us know.
And I- Yeah, we should. Which one's people to right now?
But imagine I.
Yeah, that's good for now.
So what's.
You're not anxious.
I've been wondering, yeah, no worries. Oh.
There is a.
Fingers crossed. Oh, really? Okay.
Oh, years.
Yeah, yeah. Okay.
So, I guess.
I think so. He was working.
So the deadline anyway, right?
We just put it on. NHLBI.
No,
EO one.
But
You're slowly making their way down.
Yeah, just be right here.
Yeah.
Yes.
I think Sarah will be, oh, yeah, well, plenty of light.
Mhm.
And maybe this is where
Okay.
being mostly in that longer, and working there's a project in yours on theirs.
Mhm. And it seems like it was supposed to be like, not like broad per se, but not so specific, but part of the like training program is to like develop
Yeah.
that. So-
There's a lapel also.
I think it's doable, but.
Almost.
Yeah.
Yeah, here.
Late last
year. I'm sure if I use information, it's not.
You need to support.
She had in mind.
I wonder, do you think? if I say it from
Yeah.
my phone into the microphone?
Yeah.
We'll see. But they should.
A year late.
Yeah.
I mean, there'll be other.
What I'm gonna do, because I have a lot of COVID.
What?
Oh, let's try to do-
Yeah.
Yes.
Yeah. And then you already have all the pictures and things, so.
Are those on the line?
No, that's what it's.
Okay.
Yes.
That's cool. Looking forward to hearing. Thank you for leading.
Yeah.
Me too, yeah. Oh, I mean. Yeah.
Well, but she needs all of it.
I just need to know what I need to do, like, do I have to hold the microphone?
Yeah.
Yeah.
But there's no problem.
All right, so each person goes up and they're grabbing the microphone.
Yeah, and I will give it to you.
And then what about changing the slides?
Grad students have gotten that.
Yeah, just.
For fun. It's a great laugh. That's fine.
Two days.
I know, right?
Dark in here.
You can also turn off the lights if you want. I mean, I have some complaints, right? So, we'll see. We need to actually.
Yeah, there's light chair, right? I feel the stand there.
Whatever, you want to try.
Yeah, because my focus on.
So we would like to get started. I know there's still a few people upstairs lingering after lunch and networking, but that's okay. But we will get started on here because we have a tight schedule. And this is our third round of lightning talks. And I'm looking Jeremiah Brown is first. The way this works is that you will be called up here. You have 3 minutes, plus minus 20 or 30 seconds. But after about 3 minutes, you'll hear the chime go off. And that means like you have another 20, 30 seconds to finish up, exit the station, and for the next speaker to come on. You have a handheld microphone. If you prefer lapel, we have that too. And of course, a clicker to advance your slides. The slides are all loaded in the order that the presentation should go. So we can sit through them one after another in time to finish by 2:30 or so. With that, I'm going to give it over to Jeremiah. And we'll have where the clicker is. This isn't the way we can do it.
Am I the next slide?
Sorry, that's your comments. Yep, there we go.
No, so that's it.
What's this?
I am Ron.
I think Matt, you are in there, you were inserted last minute.
Because I submitted my slides.
Yeah.
Okay. This is kind of against me.
So I give you the southern pine beetle. Dendroctonus means tree killer, and D. frontalis is exhibit A. These trees were all killed within a few weeks' time by thousands of southern pine beetles who coordinate their mass attacks like so many little tiny wolves to overwhelm the tree defenses. There can be thousands of infestations like this in a year in a single national forest. It's impossible to imagine what the southern pine forest would be like were it not for the presence of this native species. In the early 1990s, I began working with a team who asked the question, why is it the southern pine beetle? Why doesn't it occur further north than it does? And we spent years, evaluated many hypotheses, and a pretty satisfying answer emerged that it's the coldest night of the winter that limits the northern distribution of the beetles. And then in the early 2000s, the southern pine beetles conspicuously extended their distribution into the New Jersey pinelands. They marched north through the New Jersey pinelands. Within 10 years, they were on Long Island. Last year, we were catching southern pine beetles in New Hampshire, Maine, upstate New York. And so the forest height that we know as the pitch pine ecosystem, which is restricted to the northeastern US, is in danger of being extirpated by this range expansion, which is too bad. But this is why. The blue dots show the coldest night of the winter since 1960 for a couple of sites in New Jersey. Every place we look looks about like this. And the red band is the zone where it's cold enough to kill southern pine beetles. So it regularly got cold enough to kill any that might have been there, and that doesn't happen anymore. But wait. The southern pine beetle is just part of the story. The animation in the upper right shows predicted changes in the USDA plant zones as a result of climate models of changes in the coldest night of the winter. We can expect further warming of 10 degrees Fahrenheit or so. And this means that there are going to be hundreds of other species whose insects, plants, many organisms whose distributions are currently constrained by winter cold that are going to be expanding north into our forests and fields. So that means that we can enjoy spicebush swallowtail butterflies in our yard. You can plant a sassafras tree that the caterpillars will enjoy eating, but it's also going to mean more new tick species and inevitably the expansion of some species of Qulleq that are important vectors of some very bad human diseases. So buckle up, this is the efforts.
Now.
And let's not.
If you hold it very close, you want to.
It's okay. Can you?
No.
No?
Let's try the other one.
Try the other one.
Right, that one. Okay. Good. All right, so. Yes, about a year ago, we launched the Dartmouth Center for Implementation Science to essentially create an academic home around the discipline of dissemination and implementation research. The importance of this is that the field has been rapidly growing over the last 20 years with annual federal funding, not including the Corey, is at around $3 billion annually in extramural funding. And it's increasing at a rate of doubling every 2 to 3 years. Dartmouth, however, is not being very aggressive around getting extramural funding and implementation research. We have a handful of faculty that are doing a great job of working in the field. And the hope is that the center can sort of help create this academic home around implementation science to foster growth in extramural funding and also growth in the academic knowledge around and training of implementation science. So this is our team. I'm the director and two co-directors, Kelly Athroder and Sarah Lord, both in the departments of psychiatry and also biomedical data science. And we have a new manager, Julia Shaw, that just joined us from UVM. And then we have on the top our internal advisory board. So Dwayne Comdu, Dean of Geisel, Margaret Karagas, that you heard from earlier today, Chair of Epidemiology, Steve Bernstein, who's the Senior Associate Dean of Clinical Research, Marty Bruce, who's Vice Chair of Research in the Department of Psychiatry, and Joshua Davis in the Provost's office. And we're doing a fair amount on campus. So what we're trying to do is both foster an academic home and focus on faculty, staff, and student training in implementation science. And so we have a fundamental series that is launched that meets on the second Tuesday of the month from noon to 1. That's virtual and sometimes hybrid, depending. We just had some speakers from the National Implementation Research Network that focused on early childhood development and educational STEM interventions on campus that left this morning. And we're doing a fair amount of work in collaborating across campus, not just in sort of healthcare and population health or health in general, but we're being aggressive about working with faculty from the other schools. So one example is working on rural STEM education with Vicki May and Michelle Tyne on trying to scale up their intervention and using implementation science as a vehicle for that. Also collaborated with Tuck in organizational behavior and operations management to do work on that side as well, and starting to foster collaborations with Irving. Implementation science is really sort of taking the no to the do, which was coined by one of our recent WISP students. It's really sort of trying to bring a science to how we can do things better, and then also learn about identifying facilitators and barriers of an intervention, and also focus on how we can sustain an intervention. And a new emerging aspect of the field is specifically focusing on de-implementation. So how do we de-implement a certain intervention or a certain practice that we need to get rid of, like beetles? And so this is sort of our roadmap. So we want to create this academic home focused on sort of research and training. We're also in the process, I get 20 seconds, of launching, going through the approval bodies to launch a new online or hybrid master's program in implementation science that will be the nation's first standalone master's program in implementation science. So that is forthcoming, and we'll be engaging partners with that as well. So thank you, and have a good day.
Next speakers, Irving, what are Abrahamians?
Close enough. Yeah, Abrahamian. So,
Okay.
yeah. Thank you, though. Can everybody hear me? I don't really like using this. What I do has some things related to energy, but I'm not 100% sure, to be honest. I didn't learn how to use this. I'm an organic chemist, so I play with these types of molecules, which I'm sure most of you haven't seen since your organic chemistry courses. The pointer is not necessarily working. There's a bond over there, which is called a carbon-nitrogen double bond. We make this double bond rotate. It's a very simple rotation. It's a 180-degree rotation. This is actually happening in your eye now. Cis retinol is rotating like this. This is why you can actually see me. So we're just basically more or less doing the same thing using these molecules. But we're interested in using the geometry change that comes with these molecules to do interesting things. For example, we can take these and put them in polymers, and then we can use light to make these polymers basically bend or unbend depending on the radiation wavelength we can use. So you can think about soft robotics being developed with such technology, where you don't necessarily need batteries, you just need sunlight to make these robots basically work. So this is one of the things we play around with. We also take these types of molecules and put them in liquid crystals. Liquid crystals are these organized molecules you can find in liquid crystal displays. This liquid crystal over here has a particular structure. It's opaque. It's reflecting near infrared light, which is heat. We can switch the molecule inside of it, and we can change the structure of the liquid crystal, and now it's transparent. It can let the light go in. If you want to think about, for example, windows where they are smart, and based on the wavelength of light which is hitting the window, it can open up and close, reflect the light or not. There's no batteries involved. There's no electronics over here. These are just simple, cheap molecules, basically making this liquid crystal change its structure. That's another thing we work on. And finally, when we switch these molecules using light, and we have to basically optimize this and so on and so forth, we're putting in some energy, we're storing some energy in these molecules, and the question is, can now we use different techniques to release this energy later on? So we want to take solar energy, tap it into the molecule like a battery, and then release it later on when we want to heat water. This is not going to be in your car. This is going to be basically in, let's say, developing countries when you want to heat your food or boil your water, and you want to use a renewable energy source to do this and not rely on coal and gas and so on and so forth. And of course, we have to optimize the system in order to do these things. Yeah, this gives you an idea of the things that we do in mind. Thank you.
Very much on time.
It's easy. It was lovely, 3-minute on that. So I call it an advertisement, which is fine. So let's see, where's the quicker. All right. So broadly,
what I have done for my entire career is to think about network effect economics. And so the strategies of kind of large technology firms, well, how does Airbnb, Uber, SAP, Salesforce, et cetera, work? Like, why have they become huge? Why is this why are the $1 trillion market cap companies that are new no longer oil and gas, but now they are tech? And so that's been my background. I pivoted a couple of years ago to thinking really hard about business to business, which is a much more complex environment. And that automatically puts you into how do you harness data in an industrial setting? And it turns out that we're not likely to see the same winner take all and rise of the tech giants that kind of dominate that landscape as we've seen in the business to consumer. And so what we've done is we've assembled about 400 examples to really get the archetypes nailed down. And then we've surveyed about 300 people and interviewed maybe 40 or 50, really to try to understand, well, what do you do with this technology? Like, what is the core problem that you're trying to solve? And I get invited in to give a lot of talks to try to work with these companies to help. So the challenge is they all want to take advantage of these fancy business models they see in B2C. You land and you discover, no, you can't have that. I'm sorry. You have to fix your infrastructure. There's literally a data infrastructure in every incumbent firm that's older than, say, 10 or 20 years. Even tech giants incur this almost immediately. And so you work a lot to try to help them rebuild horizontal data layers so that they can then take advantage of this data. And then the first thing you always see in the industrial setting, and that'll be logistics, transportation, manufacturing, chemicals, energy, is that you harness it then for operational improvement. And in that context, operational improvement may as well be energy savings. I mean, they are mapped nearly one for one. And so I've been really fortunate. That's kind of my background and context. And I was able to get 3 really smart people. So I've got Ben Amo, who came from from Ghana. I've got Varsha, who was a railway engineer in India, and Scheideler, who's actually a Master of Engineering Management student from 2017. And they're literally applying this in industrial settings. So Ben is working with McFadden, which is a marketplace design firm, on designing EV circular supply chains. Varsha spent her summer working with Sight Machine and applying large language models in an industrial setting for energy and manufacturing efficiency setting, and is now working with Tacit, which is a firm that specializes in essentially energy industry expertise to try to capture it before they all retire. And Scheideler is working on a project, a couple of them, one with Klaus, who's up here, on models and a background for deep uncertainty in the household energy transition, and then also a lot of data analytics and improving ship and ship operational improvement. The bell went off. Next.
Thank you. I think I'm gonna depart a little bit from common practice and just talk about one paper that I wrote. It was with Sophie Wang, who was a student in my social entrepreneurship class in the winter of 2020, the last term before the pandemic hit. And I have always been interested in the overlap between the public sector and the private sector. And something that you may have heard of, corporate social responsibility, reflects a new blurring of the distinction between what is public and what is private. So public goods, and we've been talking about a lot of things that are public goods today, are non-rivaling consumption and non-excludable by the producer. Non-rivaling consumption means that my enjoyment of a clean environment doesn't do anything to diminish your ability to enjoy that same clean environment. And non-excludable by the producer means that once someone has committed the resources to cleaning the environment in some particular way, they have no ability to provide it to you, but not also to me. And so, unsurprisingly, private markets are unable to supply anything close to the optimal amount of public goods. So the public sector typically takes on the responsibility for producing these public goods. And over time, whether it's because of dissatisfaction with the amount of public sector provision of public goods, like we are underinvesting in clean or decarbonized environments, or to preserve some measure of choice, which seems to matter in the United States and similar countries more than it does in some other countries, there has been a wellspring of encouragement for private citizens and now corporations to get involved in corporate social responsibility. As just one indication, in 2011, only 1 out of 5 companies in the S&P 500 produce something that they call a corporate social responsibility report. That number has been up to 90% or possibly even more in recent years. So what we do is we ask the question, what happens when both voters and consumers jointly determine the level of public goods? Right, this is the innovation that's occurring. And the answer, and this is the surprising piece, is the cautionary tale, is that voters can more than undo what the consumers contribute. That seems like it's contrary. And the reason is that corporate social responsibility, a dollar provided through a corporation, is identical to a dollar provided by the voters. Okay, so it substitutes for it, but also it conveys an implicit tax on public provision. And that's the part that's underappreciated. And that's what we hope to illuminate through this work. And so the message, in case the bell goes off, is that be very careful about promoting corporate social responsibility in markets where it doesn't currently exist, if your objective is to increase the total amount of public goods provided. Okay, so how does this happen? So just suppose that corporate social responsibility decisions are made after voters have decided on how much revenue to raise for the public goods through the tax system. Generous voters, less CSR. Stingy voters, more CSR. And so if in fact CSR responds negatively to the amount of publicly provided public goods, and if voters realize this, then the marginal benefit to a voter of voting to raise taxes on himself to support public goods goes down, and as a result, the equilibrium is reached at a lower level of public goods. So the way forward in this is not to encourage CSR blindly, but to encourage CSR after having secured commitments from the voters or the public sector, not to reduce the amount of publicly provided public goods.
Okay, Lynn Howell. Okay, great. Well, hi everyone. I'm Caitlin Howell, an assistant professor in the epidemiology department at Scheidel, and I'm an environmental epidemiologist. So I study how metal exposures impact maternal and child health, as I'll talk about. So I look at a variety of different metals, some of which are shown up here, which we can be exposed to through many different sources, including air pollution, contaminated drinking water, food, and even certain cosmetics. And so I don't look specifically at climate and health, as I'll talk about, but I think there's many ways in which climate and health intersect with this work, and that a lot of these exposures may be impacted by climate-related events. So we'll see changes in air pollution, drinking water, and our food sources. So I'd love to think about ways in which, if any of you are interested, we could collaborate to think about how climate and health intersect with this. So specifically, I'm interested in how different metals impact maternal and child health. I look at birth outcomes, growth and adiposity in early life, and cardiometabolic health of both the moms and the children. And of particular interest to my lab is looking at mixtures of these metals, because we're not typically exposed to just one metal at a time, but usually a collection of different metals from different sources of exposure. And it can be really tricky to tease apart with these mixtures which of these specific components is leading to these different endpoints. But there have been advances in statistical methods over the past decade that allow us to tease apart which of these components in the mixture are causing these different health endpoints, and do we see greater effects from these mixtures than we would expect from just the sum of their individual effects. I'm also very interested in understanding what are the mechanisms by which these metals impact these different endpoints. And we focus in particular on the epigenome, especially extracellular microRNAs. And I'm also very interested in solutions. So if people have already been exposed to metals, is there anything we can do to prevent these downstream consequences? And in particular, I'm very interested in nutrition. So can we use nutritional interventions to prevent or reverse some of the effects we see from these toxicants such as arsenic? So I conduct this work primarily in 2 different pregnancy cohorts. One is based in Los Angeles called the Madre study, where traffic-related air pollution is one of the main environmental health threats and a source of metals exposure for that population. I also work with the New Hampshire birth port study based here at Dartmouth, and that's a study of private well users. So drinking water is a main source of arsenic and other metals for that population. Increasingly, I've also been working with the ECHO program, which is this large consortium of multiple pregnancy and pediatric cohorts across the United States. And this has really opened up some new exciting opportunities to address some of these questions on a really large scale and across diverse cohorts. So that's been an exciting development. So my email's here, and I would love to discuss potential opportunities for collaboration and look forward to the rest of the class. Thanks.
Jeremiah Manning.
How do I advance it? Hello.
Hello.
I'm Jeremy Manning, and I'm somewhat of an outlier here. I am not a climate scientist. I'm a psychology professor. I live over at Moore Hall, and I run a lab where we study learning and memory. And over the past few years, my lab has had kind of a special focus on education technology development, where we're trying to figure out ways to kind of more effectively and efficiently get people to teach or learn or communicate with each other. And particularly in, like real world classrooms, online courses, that sort of thing. So I'm here for kind of 2 reasons. One is I like living on planet Earth, and I'm generally in favor of initiatives that advance that possibility. And second, I see climate science as one of a growing number of fields that are just really interdisciplinary and fast moving. And that means we have to think carefully about how we're going to train the next generation of scientists, including climate scientists. And also it becomes harder and harder each year to do that, to kind of reach the cutting edge. And so I thought I'd kind of do a whirlwind tour of a few of the projects that we work on. We build all these tools for kind of teaching people faster. So some of our tools are like building large language models for serving as automated instructors or teaching assistants to help people, students learn more effectively from online courses. And we have kind of hardware versions of that too, where we use like, wrist-worn sensors or, cool. Or 3D printed brain headsets. We also build models of communication, like if you want to communicate something, how do you do that effectively? How do you convince people of the things you want to convince them of? I also teach a number of courses myself, kind of MOOC style courses on potentially climate science relevant things like data science and data visualization and programming and whatnot. And we also partner with kind of various organizations that share some of our values. So Neuromatch Academy runs these kind of massive online courses, teaching things like deep learning. And then Climate Match Academy is a kind of offshoot specifically using these tools for climate science. So we partner with them, kind of using our tools to help make the materials better. If you're interested in any of this stuff, I hope you'll check out my lab website or get in touch or come talk to me. Thanks.
Jackie. Thank you very much.
We're talking about the center.
Yeah.
We just. Hi, everyone. I'm Jackie Wernemont. I'm a professor in film and media studies, also affiliated with quantitative social science and women, gender, and sexuality studies. I describe myself a lot of different ways, including I'm a historian of data. I also teach people about the history of science and history of computing more generally, and thinking a lot about different kinds of impact. What I'm going to talk to you about today is also an installation that I hope you'll come and play with me later this afternoon at 4 o'clock called Energy Pools. Energy Pools was created along with Rachel Florian and Caroline Casey, who were both QSS graduates of 2021. And in a minute, I'm going to try to also make it possible for you to hear data. So one of the things that I do is I think about how hard it is to intervene in a graph, right? So if we're talking about climate science, if we're talking about, I mean, honestly, anything that we use data science for, when we show people graphs, that does a certain kind of work, and it's often very useful, but it's really hard to feel like you have a point of entry. And so with Rachel and Caroline, along with a then graduate student from my previous institution, Arizona State, named Nikki Stevens, we came up with Energy Pools. Energy Pools was a project, the materials were funded by Irving. And the idea here was to think of a way of visualizing or visceralizing. So I call these data visceralizations rather than visualizations because you can engage with them. I have colleagues who sometimes call them data physicalizations. But this is data about 2018 energy usage in the United States. It is a three-dimensional object, roughly 8 by 2-ish. And on the exterior is the energy usage by type for the United States in 2018, which was 101.3 quadrillion BTUs, right? So they're known as quads in the industry. And so up on this structure, there are 10 strands representing each quad, and they are colored by the energy source. So what you see here on the front, particularly over here, right, the black and blue, black is for oil, blue is for natural gas. If you were to go around the corner, and you can kind of see it pooling down there below, red is nuclear, coal is gray, and renewables are green. And what we wanted to do was not simply give people a way of physically interacting with the 2018 data, but also to think about that intervention point, right? So on the interior of this piece is the green that you now see pulled forward. This is post-transformation. Essentially what happens in this is an interactive group, hopefully you, we will work collectively to braid back the polluting energy sources and braid forward the renewable sources that have been identified by the IPCC report that would cap global warming at 1.5 degrees centigrade by 2050. So here you can see it. This was installed out at in Irving, California at the National Institutes of Science. You can see one of the participants there is actually doing the braiding, right? As you braid that back, you instead get to see the green sort of cascading forward. And I just want to give you a sense of what I mean by intervening in a graph, right? So it's really hard to intervene in that same information up here on either the left sides. Let's see. Oh, yep, the next one. So I'm going to take my 20 seconds real quick to play you. I also sonify data. And this is just it's a tiny little clip. It won't make any sense, but to give you a sense that there are other ways of interacting with data. So that is also sonifying data. I see people nodding their heads. And that's a shift. The pickup and pace and tone is a shift to increasing renewables. I'm happy to talk about more things in the future. Thanks for having me. Bye.
Dr. Chanky's art piece is upstairs. There is going to be an art walk this afternoon if you would like to participate in that. That follows our lab tour or champagne walk later on as well. Our next speaker, look at my cheat sheet. David Freeman.
Hi, everyone. My name is David Freeman. I'm a student of Dimitri's Giannakis over in the math department. And I'm going to talk about today is based on research done by us two and then Joanna Slinska, also over in the math department. I'll just be talking about basically modeling unknown systems in a climate system, but it kind of has more broad application as well, as you'll see. So just to kind of get some background on the problem, when you have climate models, right, you have these massive systems, these massive models that have all these different subsystems. And for certain subsystems, so for example, on the left there, maybe you have like good information. So in this case, it would be sort of like atmospheric data about wind direction, about sort of heat transfer. Generally, on the large scale, those equations are pretty well known and pretty consistent. But then a problem that you might get is you have smaller subsystems. So for example, cloud formation that are much more complicated, much more sort of computationally expensive to run, even if you do have good models of them. And sometimes you just don't have very good models at all. The problem is to run a climate model, you need all these systems to be interacting. So you need to come up with approximations for the subsystems that you don't know the equations for. So sort of at the bottom there, there's just kind of like a simple example, which we use to apply to, which is a rewriting of the famous sort of Lorentz 63 system. It's a dynamical system, the sort of butterfly fractal. And there you can see we have sort of like what would be like the known equations, which might represent, say, the atmospheric dynamics. And then that last equation at the bottom would be sort of your unknown dimension, which in analogy might be the equations governing your cloud dynamics. So in order to try and like get around this problem, you need to come up with a way of guessing what your unknown variables are. And so they can be sort of dynamically coupled with what you do know to complete the model. And the way we go about doing it is sort of assigning to the unknown variables, assigning to the unknown variables this sort of quantum state, which sort of contains information about the probabilistic information of what your unknown variables might be. And so that's sort of represented down by the bottom here. So the bottom line, and up at the top line, sort of running across the top there, would represent sort of the known equations and the things that you do have information about. And so sort of our method for resolving this problem is, again, having this sort of quantum state of probability information about the unknown things and coupling it so that the things you do know affect your quantum state, and then your sort of quantum state affects the model variables you do know. And so you can sort of complete the equations and evolve the system forward. And I say quantum state not as an analogy, but to literally mean that we sort of do this in the framework of quantum mechanics. We use the quantum mechanical sort of mathematical framework to sort of define these probability densities. Sort of it's like a different form of probability theory. So just to kind of show some results here, this is the full system of described by the equations that were in the first slide, if you knew all three of the equations. And that's sort of like a visualization of how the system looks. And then on the right there is our method applied to what was on the first slide, just the two equations and then not knowing the third. So this is with sort of our method filling in the gap of the unknown equation. Some of the uses for this include like what we talked about, like cloud microphysics, maybe convection models, but it actually applies in general to pretty much any dynamical system. So one can imagine using it in economic modeling, soil modeling, ocean modeling, anything where you have subsystems that you don't have good equations to describe. And there's just the paper that goes with it. So thank you.
Hi. Hello, everybody. I'm Zenobia Tolunti from Studio Art, teaching architecture. This is my work. It's an ongoing research project with aim to proactively address the rapid and intensifying environmental crisis. Techno-ecology offers a critical visual framework for futuristic designs that evaluate and reinvent the connection between people and nature. Here we see an example, cyber garden, a design of a ceiling where plants and people coexist. And the plants arrive depending on people's care and empathy. My artistic installations are future architectures that people could allegorically and practically inhabit. By means of futuristic designs, I explore tangible approach of bioarchitecture and bioart, envisioning a more humane environment. Such will not rely only on technology, but also on community rituals and vernacular elements of human culture. Another example of my work, Silenscapes, envisions a future architecture, which is a hybrid of a seed bank, a sharing economy, and a museum for plant species that may disappear. The native seeds in this structure are shared among members of Silenscapes rather than belonging to private corporations. The design of the experience transforms the anxiety of the dystopia of the extinct plants into the experience of a positive, optimistic, futuristic architecture. The immersive installation is designed as an infinite space with kaleidoscopic of mirrors and agrarian sounds, and construct a perceptible space that serves as a portal between reality and fiction. This dollhouse experience can potentially empower every individual to affect and influence on their own terms the ongoing environmental crisis. Overall, my work, the structures I design, can help us change our attitude and perhaps create the more sustainable communities to live in. Thank you.